Thank you to our sponsors for today's video, Ionna, InfyPower, and Eaton. Ionna, North America's premier charging network. With unmatched commitment to elevating the customer experience, Ionna is opening America's roads to all EVs, giving drivers the coverage they need, the reliability they deserve, and the amenities they crave. Also, InfyPower, the largest EV charger module provider with over 3 million power modules running reliably worldwide. Their latest G2 collection features ultra-high power density and efficiency for EV charging and energy storage integration. InfyPower, innovation for your power. And Eaton. Eaton is a one-stop shop for implementing reliable and innovative EV charging infrastructure at your site. Across all applications, Eaton's EV charging infrastructure, hardware, and software gives you the scalability, flexibility, and intelligence you need to charge today and scale up tomorrow. Learn more at eaton.com/EVCI. Hello and welcome to another Out of Spec Reviews video. You join me and Jordan here in Newark, California at Lucid's HQ engineering, bunch of nerd stuff going on. And that's the premise of this video. Jordan and I flew here to charge the Lucid Gravity. And if you want to just see the results, you can head to our Out of Spec testing channel where we have all the graphs and charts of it charging in boost voltage, charging at Tesla Superchargers essentially, and at its native voltage where we got it, 400 kilowatt charging, amazing curves, all of that stuff. This video will have the data, Jordan, I think, right? We'll throw it in.
Some of it, yeah.
And but we're also going to go through like the actual technical components as to how especially boost charging works, motor design, inverters, just power electronics for the vehicle in general. It's really a powertrain deep dive with our buddy Emad, who's SVP of Powertrain here. He's been on our channel, longtime friend of mine, and this is why I love our job so much, Jordan. Lucid has just opened the doors to us, and they said, you know what, come meet everyone responsible for the team. So not just Emad, but like everyone on Powertrain, essentially. Learn as much as possible, and we're able to film like some of it.
Yeah, that's the challenge. They opened the curtain quite a bit, but there's a lot that we just couldn't really show on camera.
But what we can show is still freaking epic, and no one's ever seen anything like this at like any other car company.
Right.
And so they're being so transparent with us because they're like, okay, who else has the nerd viewers on YouTube? Well, it's kind of us.
Right.
So love it, and we're gonna go in, and it's gonna be like a 2-hour long video, and it's so authentic. It's just us going on a tour with the Powertrain team here, talking all about charging the Gravity, what makes it drive, battery pack stuff. And if you're into electric cars, regardless if you like the Gravity or not, you're gonna learn something from this video. I learned so much. So Jordan, in the last video, we had a Lucid Gravity over in that corner of the parking lot where Emad Sapphire is sitting right over there, which is pretty sick. We rode in that last night. It boogies. Oh no, send it. See, you can hit it now.
Yeah, we got to dinner quite quickly.
Yeah, we really did. And so, we've done so much Lucid stuff. We've logged so many miles in Lucid. The Gravity is really the new, sort of going to be, I think, a higher volume model than the Air. It's a 3-row. It's engineered incredibly well. We've already driven it. We've already gone on full tours. Watch yesterday's video if you haven't. Just Jordan and I talking about all the updates since the last time that we saw it. And the charging performance is something really impressive here. So in this video, you're probably gonna have some stuff with me and Jordan back at the office here inside of all the buildings around Lucid. I just wanna say a huge thank you to all of the engineers that we met here. So many out of spec viewers, just at all levels, Jordan.
Yep.
It was crazy.
A lot of nerd people, and we met so many people.
So many people, and everyone was super friendly, super open. We probably saw way more things than we should have ever seen and can never talk about. Otherwise, they won't let us leave.
Which is fine. You want to move here.
I want to move here. It was just so cool. And the thing that I love the most, Jordan, is that we do really unique stuff with cars. Of course, we run them to dead. We do I-90 surge things where we're constantly driving and charging. And it's so cool to see them engineering the cars around the weird edge use cases that we find.
Yep.
And so 10% challenge is a big thing here. So like Gravity's charging performance and range and efficiency was really influenced also by our 10% challenge, which is cool. And you're gonna meet the people responsible for this. You're gonna see our entire process going to test the car. So I don't even know what videos we've filmed, but let's roll the tapes And if you're a nerd, if you're an EV enthusiast, if you're just into cars and engineering and how companies build cars, this is just going to be a really fun video. We had no idea what we were getting into, Jordan, when we got here. And now we've got a couple hours of footage.
Good luck.
Enjoy the video. Guys, we are inside one of the cool conference rooms. This is actually where we spend most of our time when I come here. And this is Emad Dlala. He's responsible for, well, now SVP of Powertrain at Lucid, which encompasses motors, battery, charging, what else?
Charging, as well as I also lead efficiency, range, all strategy and testing and optimization, and I also lead the HVAC team, the the thermal strategy and cooling in the vehicle.
So all the stuff we care about is why we've become friends over the years and learning so much from Emad all the time. But we thought it would be really fun is to show, we came over here to charge the Gravity, and there's a bunch of little cool technologies that go into Lucid in general, but also the Gravity. And I thought it'd be cool to like go on a tour of some powertrain stuff, maybe you can show us things throughout the video that our viewers will find interesting.
Yeah, very cool. Of course, when I joined Lucid in 2015, the state of the art was mainly, I would say, conventional architecture of permanent magnet, but induction motor was dominant because of its simplicity in many ways and low cost and no dependence on a rare earth material. But the evolution of electrical motors changed it from the motor side, electronics back then, IGBTs, silicon-based, switching was the main, device that's used for inverters. Gearbox was this triaxle, conventional. Many still companies use it.
Yep.
With Lucid, we really took a step back and said, let's rethink what a powertrain can be. But it's not like just to be different and exclusive. It's just to be better. And which sense, if you look at you've been in Lucid Gravity, you've seen the packaging amazing space.
Oh, it's insane. Yeah.
And then the performance, and then the range and efficiency, hugely enabled, of course, by the powertrain. And, and these are the motivations back then, how and why we invested so much in science, hiring the best talent. And with that in mind, we really think we introduced a new revolution in electrical vehicle powertrain world. We're super proud of what the Lucid Air has achieved in range and efficiency. Gravity takes it to the next level with its form factor, utility, space, and third row, space. And of course, Lucid is very ambitious. We keep pushing the boundaries for the next platform, which is the mid-size and beyond. We talked about Atlas in the past, which is the next generation of drive unit. And that takes not just performance, efficiency, and range, but cost, simplicity, elegance, scale to the really next level. And in this room here, you see some of our competitors.
It's really cool. We've never been able to show
this
before, but I'm glad we are.
We showed it in some glimpses in some videos in the past. But I think, of course, we respect what others do, and that's why they're here. We really think many pioneering geniuses have come up with something amazing. But as I said, Lucid took it to the next level.
Let's show the viewers this chart here, Jordan, because this is pretty crazy.
Yeah, so this shows basically the power density, which means how much power you give it with a given weight. And here we are talking about really, especially for the let's say the top one is the motorsport, and then the lower ones are our normal EV, electrical vehicle applications. Which includes Lucid Air dual motor.
So that'd be Sapphire.
Would be Sapphire twin rear. And then the rest is this one, the single drive unit used in Air and Gravity. And the rest are our, some of the competitors, or basically the benchmarks, you could call them, maybe not competitors. And the benchmark here shows, of course, the one European brand here, taking the power density to a really high level, But this is a very low volume. He was
volume
speaking as
and
very
expensive.
very expensive, very low volume. And the other ones we're speaking about ranging from 2 to 4 almost horsepower per kilogram, where Lucid is at 9.
Yeah.
Basically,
So more
roughly
than
3
double.
times. Yeah, 2 to 3 times higher power density. And this is enabled with really lots of IP that Lucid developed and patented along those years, and which we can talk about. So if you can show here
let's
some
run
of
through.
some of the
so
competitors.
We have like OG stuff here, that we're all familiar with. Coolant delete needed on every single one of those. I said it, not you. And then you've got some other cool stuff around.
You can name it.
Yeah, so like this is what powers the back of my Model S Plaid, for example.
Yes.
We're going to show everyone the Sapphire motor, which is a whole other level.
Yeah, that's a Hyundai.
Yep, this is the Hyundai
Ioniq 5.
Ioniq 5. So that's still, there's some interesting things going on. That's the front one, which doesn't do the boost stuff.
Yes.
But we're going to talk about that with Gravity boosting for charging.
We actually have the one with the boost in the rear somewhere else.
Great, amazing. And it goes through, this thing's got to have a 2-speed in it. So, it's still interesting. This is actually the old unit. Porsche's developed a new rear drive unit for this particular one. This is something I think our viewers will be interested in because the Rimac Navara, this is the rear drive unit. Still I don't know, are they tri or quad motor?
They
Navaras? Quad. Yeah. But this is the rear unit.
This is the rear, the big one.
Yeah, super cool to see that.
Yeah, very cool. Anyway. Yeah, they're a great company, innovating.
And then EQS, which is like from an NVH perspective, really impressive and smoothness, but also so many other things. And look how big it is. And I think to give everyone a little bit of context.
Yeah, we should show them the Lucid Air
y'all have been
and
doing.
the Lucid Gravity drive unit, which is, it still uses fundamentally in terms of material and sourcing of these components a similar supply base in a sense. However, because it's all designed in-house and we used several new architectural ideas to compact both the motor, the inverter, and the gearbox. We led to something really you can put in your suitcase.
Yeah, our buddy Nick just carried this in here.
Yeah.
He literally just picked it up and put it on the stand from the front area. It's amazing.
So we're going to show you maybe a section of that. This is the twin drive unit, which is dual basically in the Sapphire.
Is it basically 2 of these, or is it totally different?
So it uses fundamentally the main core components that this one. Inverter, 2 inverters, and stator and rotor. It doesn't have a differential because it's an electronic differential. It has a different gearbox, different gear ratio, and you have double the torque because of that, so you have a different gearbox.
Okay.
But the core components are componentized because the economy of scale is huge. And for the Lucid Air, you have a front and rear drive unit and the Lucid Gravity. They're almost identical units with some different in the, basically the orientation of the drive unit inside the mounting system.
Okay.
Or the chassis or the
and
subframe.
gear ratio, final drive.
Yeah, some we have two gear ratios, 8.7 for the rear for pure air, and also Gravity RDU, the rear drive unit is also 8.7.
Right. Yep. And
the front is 7-to-1 gear.
So I'm sure we'll talk a little bit about it throughout the video as well. Something we bring up when we try to review cars is to figure out motor type, so permanent magnet or induction. So I want to get your opinion on how important that distinction is, but then also the switching technology going from silicon IGBT to silicon carbide. What are the benefits, the pros, the cons? Because the cost goes up. Is the benefit there? What's your impression?
Yeah, so impressions, of course, everything should be put in a cost matrix, which battery cost part, a huge factor of that formula.
Yeah. When
it comes to both silicon carbide and permanent magnet technologies, efficiency improves drastically.
Okay.
And then you look at what's the value of dollars for each mile, and you gain, and you do that formula. And I would say, for example, permanent magnet, right? Sometimes you could end up with a vehicle that has 2 permanent magnets because of need of performance and power.
Yeah.
But you could also mix. Where you get the gains when you're during cruising, during normal city driving, 1 permanent magnet, the other motor could be induction. For our, brand and, performance aspiration for both air and gravity, permanent magnet is important for thermal endurance, and of course towing for gravity and so on. But where we stand with that is like we didn't really compromise in one aspect, which is related to the back EMF. Because when you have two permanent magnets, you typically you need to turn both on at almost 60, 50 miles per hour.
We talk about this all the time.
Otherwise, you have to disconnect one.
Yep.
So for all our platforms, we always have one off. We don't energize it through the inverter. It keeps spinning without needing to inject currents to, that's a secret, and really innovation that we have in our motors.
Yeah.
And the way how the winding is designed and the inverter are designed with the power levels, we were able to not enable the second motor up till 85 miles per hour or after. And then you need it also for other reasons, to share thermal stability and all that.
But, it's a topic we bring up a lot with, rear motor connect or having to do like induction and permanent magnet. For example, we've been doing Cybertruck content, and they arrange the permanent magnet motor depending on the trim on different axles, which change the behavior of driving completely.
Well, our philosophy is really for us to keep the electric motor as simple as possible. Elegance in the mechanical architecture, electronic architecture is huge. And for us, we would like to solve, let's say, challenges through electronics. And in this case, for example, as I mentioned, we disconnect this electrically instead of mechanically, which is...
No one else does, right? As far as I'm aware?
I'm not aware.
Not at high speed.
Not on those, let's say, cruising speeds in the US up to 80 miles per hour. At least I'm not aware.
Yeah, same, me either. Most of the time, then you get, clutch disconnect, which leads to drivability issues. We're not big fan of having a clutch disconnect for, maintenance, reliability, clunk, and MPH issues. That's a philosophy. And that's why these are
for luxury brand too, right?
Yeah. So it's like the size of a watermelon.
And it was, this is 500 kilowatt.
Yeah, crazy.
500 kilowatt peak, and also what's also impressive about it, Kyle, is 200 kilowatt continuous.
Right.
So it's not just that means when you take it to track or canyon driving, this doesn't derate.
Right.
That's really important.
And the fact that
so it's not you just get some vehicles, you get one pulse of acceleration and then it's like, you get the peak power, but then does it sustain it?
Right. And this thing can just boogie. And I think we've proved that with our testing on track with air and stuff. And it, we haven't done, I rode with you in a GT Performance once, and that had a little bit more thermal capability than
the GT Performance, which is discontinued now. Maybe who knows, in the future we may bring it back for simplicity reasons. But that has a different motor configuration. So it's a hardware, not so software. So we enable 1,050 horsepower through added inverter capability, as well a new winding system that gives you that power and torque.
Yeah, but even the updates to the 25 GT that we had were great. We never got into
that one. We model year 2025 actually, which is in production today, has so much thermal capability added to it too, because you have a one motor capable of about 500 kilowatt the rear, and the front about 200 kilowatt, 150 kilowatt. And that's also due to efficiency optimization, which is the front motor, is the cruising motor, is lower power motor. And you would never, in a normal world canyon driving, derate neither of these.
No, we never derated the car. We never did a full track day with it, but we were drifting it around and never had an issue.
I remember, I think you or someone asked me, why don't you have a motor temperature in the dashboard? We said, why do we need it? It never derates.
Amazing. And then this thing, the thermal capability on this
is even next level.
Yeah.
You can have a special heat exchanger. I showed you one day. Maybe we'll see.
I held it. It was later.
Insane, like really aerospace type of. It's even the company that does that for aerospace application.
Okay, cool.
And of course a larger coolant and oil pump systems specific for Sapphire unit, and we sized all the gear systems to be very capable, to get that power and to the wheels.
We were out driving yesterday, and you punched it because you have a Sapphire. And we were next to you, and you shot off like a rocket. I couldn't believe it.
And I was at relatively low stator charge. The battery wasn't preconditioned, and all of that.
And you just boom, gone. It was crazy. So batteries.
Batteries. We have here some competitors.
I think everyone's familiar with that one.
Everyone is familiar with that. This is our Formula E. This is 18650 actually cell, which is in already no longer in production of Formula E. It's Gen 2 battery system. Though this was actually what inspired the Lucid Air and then the Lucid Gravity module, which we, upgraded to 2170 cell. We use one really innovative way to do injection molding technology for to have one bucket here, or one basically module. You only need one component from injection molding.
For the entire enclosure of the module.
Of course, there's the bus bar assembly, aluminum bus bar assembly.
And that's all baked in
this
there.
wire bonding. The wire bonders here, Kyle, are actually optimized for power. You see, one is thinner and the other one is larger.
Yeah,
that's to
explain
give
that.
one to give you a fusing mechanism for safety, but that's usually your anode is not the main problem. So we thicken the cathode side to give you the power and
very cool.
Because this you're speaking about still a very that's the same module was in the Sapphire. It's a crazy amount of
a lot of discharge power. And I've been on the production line in Arizona for this when it first went in, and it was really cool to watch. How simple and fast
I wish you guys could come actually to see. I'd love you to come to see the phase 2.
We'll be there.
Phase 2, where we automated and took that, because I know when you came there was a separate facility of powertrain. Now it's all integrated in expansion that we had in Ampoint there. A huge level of automation and the capacity, of course, increased by about factor of 4. Because with gravity launch, we had to.
Gravity's going to be the big thing coming soon. Then midsize, of course, we can talk about later on. But anyway, we've been doing a bunch of gravity stuff to the viewers, and we have some cool videos coming. That's all I'm going to say. Okay, this Wonderbox stuff. You got some cool things going on. What's all happening here?
Yeah, of course. The Lucid Air and Gravity both support onboard charging up to 19.9 kilowatt in the US here, and 22 kilowatt in other European and Middle Eastern markets. Both have bidirectional. You're a big fan of the V2V.
We use range exchange.
Range exchange.
Now, I basically need a Lucid just for our range testing.
This is. And you get 9 kilowatt plus in range exchange.
No voltage sag.
No voltage sag. It's pretty cool.
It's amazing.
And so and this is capable also right now, in the hardware to do vehicle to home. Because if you do vehicle to vehicle, that's what it's just the interface is missing to vehicle to home, and we are working on that.
Okay.
I don't want to promise over. Something will be happening soon.
And you're going to be doing AC vehicle to home.
Yes, AC.
Yeah, perfect.
We're not fan of DC because you have a separate station. Why not? You have the system.
Yeah, it can already do it.
You need it.
Yeah.
Which you have your cooling systems, you have all harnesses. Why do you replicate this outside and it's much more costly?
Yeah, totally.
What you need is only basically a microgrid disconnect system to connect and disconnect from the grid. And pretty much that's it.
100% agree.
Yes.
Absolutely. Speaking my language.
Yes. This is some of the BDU. You have your contactors, you have your pyrofuses, you have your electronic circuits there that communicates with all modules in the pack, and they do the controls.
Got some very critical over here too. Maybe you can talk about these.
Yeah, these are the silicon carbide MOSFETs. So we have, this is interesting actually. This is the cooler in the middle. So,
and that's really cool that you can literally, because they're draped in coolant, right? Or how?
No, they're not. They're not. They're actually connected through thermal material between the cooler and the bus bar.
So some thermal paste in between. Okay.
But they're very rare we get immersive cooling with electronics that way. However, it's a technology that we innovated to cool it. This is an inverter. You see 3 phases. It's 3 modules. So this is half of the 500 kilowatts. The second half is here. However, in this case, it's just a dummy inverter because we have 2 variants of inverter. One will have full bridge, and then another full bridge here for the inverter. But to allow us to design 2 levels of power and reduce cost, because silicon carbide is still expensive.
Yeah, totally.
So for example, Air GT has 800 horsepower 19, and GT Performance has 1050. We added another layer here.
So that's where the power comes
The
from.
power, and we rewound the motor in a very elegant way. I'll show you maybe in another instance where we see the stator. And that's the winder. Basically, both actually variants of motors come with exactly the same winding. The way how you connect it,
That's the difference.
which is here. This is, for example, the high power connector.
Yep.
So we will see the lower power connector in another maybe occasion when we go to the labs. But this connector has 4 parallel branches, so you can push more current inside it.
Okay.
So the
cool.
other variant has 2 parallel branches. So it's a lower power, but you still get the same peak torque. It just drops quicker.
Sure. So you get the hit. And
Yeah,
then
you
it
get the
comes
head,
down a little
but
bit. Yeah. But GTP just pulls all the way
yes.
up. Yeah.
You just extend that corner.
Yep.
For power drop or torque drop to a much higher speeds.
Sure. But I was honestly we just had the GT for a while.
Yeah.
I mean, this was a couple months ago. But even that thing,
The GT still rips.
I sent you a picture of it at 168 miles an hour at 5% state of charge.
I know.
And I was like, still it
I know.
boogies.
And this is kind of the key point, because both motors, we really, philosophically, when we design our motors and platforms, we do everything, simulations, of course, on the computer. What we agreed as a company, and even coming in Gravity and of course mid-size, is to keep, not just have this pulse in the beginning of power and torque and then dies quickly. We want to get the G-force really sustaining to high speed. So when you accelerate at 40, 60, 70 miles per hour, you feel that. And that's what also gives the air special kind of, and Gravity.
Yeah, it's unique.
That unique feeling about it. It's like always you feel that.
Yeah. Well, it encourages you to keep your foot into it because you're still, things are happening.
Exactly.
Yeah, cool.
And this is even for touring, which is 620 horsepower, plenty. But we keep that type of DNA in terms of performance. So this is our winding, which is continuous wave technology. We patented this, especially with its connections. In this case, of course,
you don't have like welds everywhere.
No welds. It's all continuous.
Yep.
Very few welds here to make the connectors. This called what the stator core or electrical steel lamination assembly, which includes the magnetic circuitry to allow for you to build the torque and transfer power from the stator and then to the rotor, which also has electromagnetic circuits. In this case, you have embedded magnets inside there.
Yep.
It's an 8-pole system. And you have 3-phase terminals which go to the inverter there. What's unique here, of course, is the continuous wave, but also our microchannel cooling. This is really super unique and super, effective.
Well, it's how you get the long power without big derates.
You're speaking about the stator of this size, okay, which is, you see the other one, which is double the power, more or less.
Yep.
And much smaller in size and much lighter in weight.
Well, and so much more elegant too.
Yeah.
Just saying. And no one's really looking at this underneath their car, but it is cool to know.
I know. Well, what the customer gets, of course, that space.
Yeah.
And that, of course, power and efficiency, because efficiency is...
We also should link in the description, Jordan, maybe you can put it into your tech talk that you did about this. Talking about how you...
The details, absolutely.
Going into like avoiding all of these like eddy current situations.
Yes, the size of the conductors, all optimization, everything.
And it's all out there, and everyone needs to watch that video because it was so great. But that's all your baby right here.
Yes.
This is so cool.
This is how I started, 2015. Back then, the state of the art was induction.
10 years ago.
10 years ago. And, Peter back then always believed in science and to bring the best minds to engineer the product. And we had the same philosophy and, made it happen. Yeah. But it's engineering is one factor, but manufacturing and scale is huge too. And we engineer a product that can be scaled. This is developed in here and made in Arizona and right now in our unique production lines.
Super cool. Should we show the cutout of it really quick? Maybe, because this is kind of interesting for people to see how things are working, the diff being so small and stuff like that.
This is the cutout of the drive unit, which includes the heart of it, which is the stator and the rotor here. You can see the rotor cuts here, the steel laminations. Inside the rotor, we embed the differential, which is a completely different approach than anyone in the market. This is patented myself, I show you, I introduce you to Balázs.
Yeah,
he's,
just
he's
met
a
him.
genius.
Yeah, super cool guy.
Gentleman from Hungary, and myself and him were working on the architecture, but how we can maximize, you know, the power of this motor with the space we have, and we embedded it inside the rotor. We made sure the lubrication. You see how you even lubricate this system.
Yeah.
Make sure it's. But
you don't have dry spots or hot spots anywhere?
No, I mean, it's all optimized. Of course, we have other engineers who work on the lubrication and cooling systems. We also did embed the resolver, which you measure the angle of the rotor with respect to the stator through a very elegant way that's no one done it, at least in production, which includes embedding the rotor of the resolver inside our shaft. And this is, of course, your reduction systems. This is a cutway. This case is 7 to 1 gear ratio. And you have here your inverter, again, exploded view. And the inverter is connected also super elegantly. Is like the connectors of the inverter, which is, I think we have one somewhere here.
Oh,
the
cool.
length of it very small. So this goes here, and the inverter from that side goes here.
Tiny path.
Tiny path, because that's a parasitic losses, and
Absolutely.
it affects your when you switch the inverter, your capacitive parasitics are so important for the overshoot of that. And then it limits your power and limits your efficiency too, because of the DVDT effect.
Right, yeah.
So everything is optimized to get that performance.
Yes, this is such a cool story too. And you did talk about this in the Tech Talk
Yeah,
as well.
we
And
mentioned
it was
it.
just awesome.
It's just
to
the
see
way
this
also
kind
how
of stuff.
we assemble it.
Yeah,
It's
and
super
interface
elegant. But that
everything.
way,
Oh, that's the heat exchanger.
that's the heat
yeah.
exchanger of the Sapphire. Yeah, it's here.
It's so crazy. Jordan,
Yes.
get a close up. Just look at the detail on all these
Thousands
like,
of these
perforations.
channels, thousands of micro
How many
channels.
kilowatts can it do, do you think?
This is about 15 kilowatt.
It's crazy.
Yes, cooling.
Yep, amazing.
Yeah, and you have a heat exchange between oil and coolant, and yeah, super effective. So you get the coolant inside the channels, and this immersed in the oil.
Just awesome. I love that. Yeah.
Yeah,
That's so
very cool.
So, okay, good stuff.
Yeah.
Most of this pertains to air, though. So what can you explain to us just quickly, because we're excited about Gravity coming and we're going to drive
Gravity,
it soon.
of course, especially the rear drive unit and also the front drive unit, we made significant changes to allow a more towing performance, and then the boost charging, and also the NVH improvements that you've noted. The Gravity is super quiet.
Absolutely. Yeah.
You know, so I think we're going to take you to the lab to show you these innovations.
Oh, hell yeah. We're going into the lab, folks. Okay, let's do it. Should
Thank
be
you.
fun.
We're just going to show you some of the important technology that we're introducing in Gravity. But first, we're going to just take a step back, you know, show your audience what we already have in production in Lucid Air and some on the Gravities too, and what we're currently bringing to production and our customers, which is the boost capability. What's a boost? Which basically, you know, charging is a very interesting and moving topic. And currently, charging infrastructure is made of different systems, which is related to compatibility with the charging voltage infrastructure to your vehicle voltage infrastructure. And how to make these compatible is very important for you to basically be able to draw power from the grid or from the charger to the vehicle. So typically, in simple terms, you have a very basically matching or a matching voltage system between your charger and the battery. And then you communicate to the charger and you draw power. But what if that voltage is very different? And in this case, the infrastructure that's being built for quite a long time has actually a specification that's not matching current Lucid Air and some other vehicle infrastructure. To be specific, we have 400 or 500 volt infrastructure, and the Lucid Air, as you probably know, and Lucid Gravity are 924 and 26 volt. So Gravity is 926 volt system. So to boost voltage up, you have to do a certain changes or certain controls changes. It's not simple. This is not just the size of the wire or your battery or your controls, changing voltage is actually quite challenging, and that's why we have transformers in the industry to step or down or up voltage. But in a vehicle, transformer is harder to control, expensive and heavy. What you could use a converter, power electronic converter, which is becoming more common these days. You could use a different way to split your back voltage into two, so you can connect them in parallel when you charge, so to reduce the voltage into half, to be able to be compatible with the 400, 500 volt charging systems, or keep them, of course, in series and do other mechanism. What Lucid did is like, hey, we are very focused on packaging efficiency, cost, of course, simplicity and elegance. To add a separate power converter to boost voltage is very challenging. To do a split back is very challenging, and also has some limitations when it comes down to battery modules or packaging systems that has a quite low voltage. When you split it, it becomes so low. And thirdly, split the pack always leads to a low voltage during early state of charge or low state of charge, which means you have to draw a very high current to get high power. And charging has been hugely critical for our customers and for EV adoption. So we really invested so much to bring the best charging experience in Gravity. And I really mean it. This is not just for performance. It's accessibility to charging work. We know Tesla Superchargers in the US and worldwide is absolutely fundamental and very important to our customers, and we signed an agreement with Tesla thanks to them for opening the charging network in the US here. But Lucid platform is not compatible with the current Tesla charging infrastructure, although Tesla is working on the V4 that's coming soon this year. However, they already put so much of infrastructure in the V3 that is very critical for us to be compatible with. And our best, and most elegant solution we found is to use our drive unit. So what I'm going to show you here, Kyle and Jordan, is our current drive unit that's in the Air, the Lucid Air, which is capable of 500 kilowatt charging power, 250 kilowatt regen power, 200 kilowatt continuous power, which the drive unit is made of inverter. It's usually, in this case, in our case, a three-phase inverter, and you have electrical motor with winding systems, and you have a motor gearbox or a gearbox reduction system. And I'll introduce the team later on who made this happen. That elegant, very compact, 74 kilogram system that's capable of unbelievable, unheard of power density is absolutely possible because of so many innovations in the winding, cooling challenge systems, and cooling, and as well as the gearbox reduction and the differential systems. But the inverter, of course, is key. And for the boost, which I will speak in detail in a few minutes, this is the drive unit that's in Gravity right now. It's the rear drive unit. We also, for convenience, we had to change the charge port from the front to the rear to be fully compatible, the right location, right position with the next charge port, as Kyle demonstrated in his charging test. And the rear drive unit is very in close proximity to the next charge port in that left rear side of the vehicle. And what we have changed is we reconfigured the inverter and the motor to be able to still accept a 500 volt or 1000 volt up to 500 amp power, which is up to 400 kilowatt, and allow the inverter to switch between 400 or 1000 volt or 500 or 1000 volt systems. And based on the voltage, sensing the voltage, the inverter controls would decide whether to do a boost session, which means up the voltage, or just bypass to go directly to from the drive unit harness connector here directly to the battery. This goes to the battery, this goes to the charge port. And I would like to say that we're super proud that this is already in production, capable of up to 125 kilowatt charging power, and with a very 225 kilowatt. 225
Which
kilowatt.
is so much more than the others out there.
I'm aware of the best 120 or 225 kilowatt
that's
with a
not what we've
much
seen
larger
before.
motor, with a much larger, bigger motors, drive units. And you've seen the charging curve by now, maybe. If not, maybe that's coming in the coming video.
Testing. It's available.
It's available already. And we sustained 200 plus kilowatt up to 50, 60, 70%, something along those lines. But we achieved this with a quite elegant and architecture. We patented this actually in 2019, myself, Dick, who I introduced very soon, to tell you also about that story in general.
But Emad, the one other point is, maybe our viewers at home recognize this or don't, the ability to basically boost the voltage through this solution rather than going with a split pack or something means that even on future smaller pack variants of Gravity with lower voltage, it means that when you plug in at 0% state of charge at a supercharger, you're still getting 220 kilowatts.
And we will show you the graphs maybe during the video. I'll ask the team to bring those graphs. You always request the highest voltage, stay there. In this case, for Gravity, we request over 440 volt, was almost the maximum. So in a normal other cases, even if it was the voltage is high, because at low SOC, you would be requesting 300, 350 volts.
Sure.
That's a significant. That's basically if you push the current from 500 to 650 because of I²R, you heat up the cables very quickly.
That you smoke the cables, we do it all the time, and then your power goes down.
So and the efficiency of this system, we'll bring the numbers, is very high because the motor is very capable of 200 kilowatt continuous power in a driving mode. It's very able to thermally be capable of 225 kilowatt in a boosting mode. And we had to upgrade the inverter and the motor and some of the other connectors to be able to do this. And we've done it in about 1 year.
Incredible.
But the patent, the concept was there. But the implementation, the execution, the testing. I want to also give big shout to the inverter and controls team. The software control team was able to make it happen despite the challenges, because boosting is very unique in that sense, because usually when you charge from a charger to the battery, you have the battery is a beast stiff charging, so
it can absorb a bunch of stuff without
all the noise. But now we have a booster which depends on your voltage and current controlled circuits or loops, and you have to make sure that controls are very stiff to any changes in the chargers, because the chargers, what happens usually, you have a few cabinets that go 150 kilowatt, and the next one, during the switch to the next one, you get a big pulse.
A lot of noise happens as it brings on power modules.
And they are very sensitive usually, the infrastructure. You don't want you have to make sure your voltage stays stable during that switch between cabinets. And we were able to do it. We're reaching 100% success rate right now, and we are very excited to have our customers.
We won't name names, but we've shown that issue many times on this channel with other issues charging with
sometimes it could stop in the middle.
Yeah, absolutely.
You start and you go shopping, you find the car didn't charge. You could sometimes fail from the beginning or at the end. It's really unpredictable.
Totally.
And we did 0 to 100%
dialed in.
Fully dialed in.
Yeah, and we had no issues yesterday.
We charged it in many places and different conditions.
Good.
Very confident. And the thermal capability of the system is super critical too. I mean, we had to make sure the power that goes, the 500 amps that goes through the inverter, it's a lot of currents. Of a platform that's designed for 1,000 volts.
This is this component here, just in case the viewers aren't totally realizing. That's the inverter.
That's the inverter, you know, here.
Yep.
And we will share details about it. For now, I want to introduce Dick. Dick has been with us for 13 years, 2011, I think.
Yeah, October 2011.
Yeah, Dick is really genius. He worked in early on. Maybe we can go this way.
Yeah.
You worked early on the BMS, I think.
Well, when I first joined, the company was really doing.
How many people when you joined? We had.
Well, I'm employee 27, so
But
there were only.
But when you joined, maybe 27 there.
There
or
were about 20. There
20.
were about 20. Some people had already, you know.
Yeah, back then is Bernie Tse was there, and Sam Wang was this.
Yeah, that's right.
Yeah, the founders.
Yeah, the founders of the company.
And you are among the founders. You should be considered founders.
It was still 2 years after they after the company started.
Yeah. But what brought you to Lucid? I'm just really curious. I never asked you all the stories. Like,
well, Bernie had been trying to get me for a while earlier when they were trying to start the company there. So
did you? I know you know Martin Eberhard.
Yeah,
huh?
yeah. Martin Eberhard. He's an old friend of mine. We went to
the founder of Tesla.
I met him in high school, actually. Yeah, yeah.
You still friends with him?
Sure. We have breakfast. Every couple of weeks in the morning. On Saturday morning.
Yeah, he's a cool guy.
Yeah.
And an interesting story, Kyle, is that the founder of Lucid, which used to be called Atifa, was Bernie Tse, used to be a VP at Tesla with Elon then.
Cool. Yeah.
He was leading the energy department.
Right.
Interesting.
And then the founder of Tesla, which is Martin Eberhard, worked for Atifa for some time too. So these companies are interestingly linked.
All near each other.
Near each other. Yes. But tell us more. So you worked in the BMS in the beginning or the inverter?
No, it was the BMS in the beginning.
Yes.
And then the company always had this vision at that time. There was not the car vision yet. So at that time,
Powertrain and
it was going to be like this one-stop shop for everything powertrain. And we were supplying battery packs to a lot of buses in China and
Yes.
all that.
Yeah.
We had a factory in Shanghai that was assembling these battery packs and testing them and stuff. And so, so we were always like reconfiguring BMSs to go into a different type of bus and partnering with a Chinese cell vendor at the time. But then, like about 2 years after that is when the company decided to pivot. And
to cars,
yeah,
to build
cars. Bernie, and got
raised some money with Peter, got Peter
Rollins,
convinced some investors to his ex-Tesla chief engineer.
Yeah,
we got the funding, and then I joined. Some other folks joined.
Right.
And when I joined, I remember, of course, the motor we had the legacy, some X design, and then you have the inverter also, some X legacy.
So I started working on the inverters originally. We call this sort of our fourth generation inverter.
The fourth,
so
which is the fourth generation, which is the first for
the first one that worked.
The product, which I love it.
No, so I worked on generations 2, 3, and of course this fourth one.
Yes,
and
we had the number 3, which was in the Alpha prototypes. That's number Alpha, and it was IGBTs. It was a very large, complex, cumbersome cooling systems. I remember that.
Starting inverter. So inverter 1, I didn't have much to do with, but inverter 2 was the first one. It was like a very large box, and that's the one we put into the Edna van.
The Edna van. I'm not sure if you know about that. You should see the Edna van.
There's videos.
You should see
about
it.
We'll overlay a picture of it.
The Edna van, and we were doing, we were taking out at Crow's Landing there, and we were doing quarter miles and stuff like that.
Back then it beats every almost sports car. But that
we were doing
van.
We were doing like 11-second quarter miles and that thing. But and then later on we were getting close to the Alpha of the Alpha program of the Lucid Air. And so that's when inverter 3 was done, and we put those inverter 3s in Edna, and we put it out on the track again, and we were testing it. But
I remember we get more power. I remember the 700 Newton meter induction motor and all that stuff. I remember
induction motor.
All the early stuff was induction motors still. And Emad was telling us, you really need to move to the permanent magnet motor.
So why? I mean, when did that change happen for Air to go permanent magnet? Was this
between Alpha and Beta?
So the Alpha early drive all were induction. During Alpha we built permanent magnet prototypes. in Menlo Park, our shop, and we retrofit some of them in the we did actually Laguna Seca back then with the Alpha. We you know, drives, and everyone is like, those permanent mannings held power very well at high speeds. We gotta make it happen more efficient. We'd start doing some efficiency testing, and we switched. Technically, we made the decision, I think, 2016, 17 to go. And then the same time we were...
you know that car that we took it up to, we went to, what was it in Ohio? The big oval up there?
The big oval?
The big oval. But you know, we did it with induction. That
was induction,
We did it with 235 miles per hour.
That's funny.
So that was inverter 3 with induction motors. That's what that was.
That's hilarious.
So, but then we really... And that was still 400 volts.
Yeah, 400. And IGBTs.
And IGBTs.
Then everything changed.
Yeah, everything changed. Yeah. And,
so I remember when you and I were discussing few things. One is the voltage, but silicon carbide discussion came first, where I would start to do some simulation. I was like, hey. People think it's like only half percent or 1% efficiency difference, 98% versus 99. But if you put it in a drive cycle, in EPA cycle, low loads, and all that's like, oh, now it's 5, 7, 8, 10% difference. It's like, and we start to do it. We do the value, battery cost, and like sell it. And then it made it even more important with the high voltage. High voltage silicon carbide are more suitable. You can tell them why silicon carbide is more suitable for high voltage. That's a band gap.
One of the big differences was, it was looking like the IGBTs at high voltage were going to give us a lot more losses. There's the, especially light loads. This is where the MOSFETs are good, because they don't have there's a minimum voltage. When you turn them on, there's a minimum voltage across them that's not there, even if the current's somewhat low, and so it's not there on a MOSFET. So light load efficiency is better for MOSFETs and silicon carbide.
You can switch them. You switch them faster if you want to. By the way, we in the boost. The MVH would be a problem if we switch at 10 kilohertz, even 15 kilohertz. So we switch at 20 kilohertz for boost.
And then it's out of the...
Yes, out of... You can't hear it anymore. Because
your dog might be angry or something.
Let's start. You know why. That's pretty funny.
Yeah.
But you have complete control over that, of course, which is super nice.
Completely. Yeah. We could switch it faster if we want to, but we don't need to. And the other thing, Dick, I remember we're discussing the cooling maker channels together.
That's right. Yeah, that's right. Yeah. I remember you guys we were trying to figure out how to get the oil in.
We showed it earlier, but the little dots that are...
the lights. So the dots between here, there is tiny dots, and it works magically. We have videos of them.
But I remember the whole trick was like, how are I going to get oil into there? And you were thinking of like grinding out a corner there down to some channels. Right?
Dick and I were exploring. It's like, hey, we could do this, but then we advanced it. This is fully manufacturable. It's all stamped, automated system to get you this stack. It's actually glued together. This made of 440 laminations, thin laminations, really thin, because of the eddy currents. And that's also patent actually together in there. And then of course we start to look at the architecture of the gearbox, where Balazs and I joined the same year, few months in between. Balazs has joined maybe 1 month. Balazs, come over. Maybe. Thanks, Dick. Really good to have you here. It's awesome. It's really awesome. It's been years. You can stay in the video.
Thank you so much.
Dick, you can stay around. So Balazs,
if you're loud, they can hear you.
So Balazs, you joined 1 month or 2 months before me. When did you join exactly? Me?
They were the 30th of June. 30th of June.
I joined August 24th. So less than 2 months. And I remember meeting this gentleman, always Balazs. It's like sitting with another gentleman called Jeremy Meyer, who was doing the integration and mechanical design of certain systems in the motor. And the three of us were exploring and discussing ideas and how we do this. And I remember very well Balazs is like very passionate to introduce and we call them the idea machine. Seriously, it's a really idea machine. And what makes sense for the system? I look at it from a system, business point of view, scaling,
Yep.
innovation. And you know, we iterated many concepts back then, the different differential concept with the high torque. We actually prototyped it, work it in certain, and we have some challenges in other ways. And then we start talking about this this differential.
Which is so crazy.
Yes, tell us about it. I know the idea is old in your mind, but then we patented together, we embedded it in the rotor, we made it happen, get the space, have this, what we call it was the joint up thinking, but like all working closely together. Either you're electrical or mechanical engineer, how you embed it, how you make sure the rotor flux and all that is optimized with the mechanical system. But Balazs, tell us your story, history,
Okay, so
geniuses.
So basically in 2015, when I had an interview with Mr. Rollins on the Ativa Lucid, then one of his interview questions was that he drew up a traditional powertrain, what we call internal triaxial design. But most of the people usually do this. You have a rotor, you have like a two-stage reduction set, and on the last stage you have a differential and it goes out to the wheels. And his question was that, okay, what is the fundamental issue with that one? And I mean, honestly, there's no fundamental issue with that design, but there are smaller issues. And I had this dilemma because I did recognize that that design is coming from his previous company, and I did know that he was the chief engineer for that. So on an interview, are you going to point out what is the fundamental issue with that one? Then I rolled the dice and said that, okay, it's statically indeterminate, which is an engineering condition. In layman's term, it means that it's over-constrained, let's say. And he started to smile, so that was a good sign. And his question was that how would I solve it? And then I raised the question back, do I have like 3 hours, 3 months or 3 years? And he started to ask that, okay, what if you have like 3 hours? Okay, you have to do this manufacturing approach. What if you have like 3 months? Flexible elemental on the bearings. What if you have 3 years? And on that interview, I sketched up the concept of the active core.
We call it active core.
Active core.
During the interview, you came up with this idea.
Not exactly. So this design was already something I was toying with.
Before he joined, he already had the thoughts about it. So
actually, in 2010,
it was realized
2009.
It was realized in Lucid, though.
but then the novelty here is that if you relocate the differential from the high torque, low speed side to the rotor level
before the reduction system, you make it much smaller.
Yeah, you can basically scale it for like 7, 8, 9, 10 times smaller.
Yeah.
And suddenly it became so small that you can put it into an appropriately designed rotor's internals. Yeah. And then this simply you have to have like 2 reduction systems, but both are just only taking care of half of the load.
Right.
So all in all, mechanically, everything else is...
So power split and half-half.
Yep.
So your systems are smaller, and your gears and bearings and everything smaller actually gets more scalable instead of one big. So we have
Proportional.
Proportional, yeah.
So just mechanically, if you have any existing motor, you can make the motor basically half the size. But then there's many other things why this motor is so compact.
But usually, here is the thing, Kyle, and this is, I always say this, conceptualization is the most important, but can be sometimes easy. The implementation and realization and ramping a product to production is the hardest.
Yeah.
And that's where we're super proud is from idea, which is fantastic idea innovation. We were able, with Alash and myself, is like, look at every detail to make, this can be noisy. They can heat up during high differential. These cars go to the track with this thing. I mean, it has to be designed really robustly, and scaled with our manufacturing tolerances and supply chain and all that, type of operations that are really difficult. But Balazs.
What I liked about that moment, that basically Mr. Rollinson did like the idea, and we had a gentleman's agreement that we are going to make it. But then quite years later, when we had the financial crisis,
This is no secret. At 2017 and end of 16, let's say 17 and 18, we went through a quiet period where, searching for next funding round, and we get that quiet period to actually step back and it's like, we have time to rethink what actually our production platform should be. So it was during that phase where we switched it from 400 to 900 volt. We switched it from IGBT to silicon carbide. We switched it from a normal cooling to a microchannel cooling, and we switched it from a conventional gearbox architecture to this novel architecture. And there was that seriously, because the alpha was completely different, and had we had the money, we would have gone with that same technology. And sometimes I always say, these things happen for a reason, and the Air was also fantastic platform to showcase this technology.
Totally.
So of course, Balazs, since then, lots of innovations, in the Atlas architecture, in next gen, the twin RDU and Sapphire was his architectural design, and next Atlas, I can't speak, single motor and more.
Tell us about the next gen.
We can just speak generally. It's going to be next level in integration, number of parts, simplicity, cost. It's the Zeus drive unit is still the best in the world class, even from scaling and volume. Really, even BOM cost of this one is really super competitive. But Atlas, of course, is the next level. So it's a mindset where we know the volume is huge. Any improvement in reducing the footprint of the production line, number of parts, BOM costs are going to be of huge importance.
Not too many people are available with this. Basically, our Zeus architecture, if you normalize it for power, it's basically way more cheaper than anything else.
And even if you don't normalize it with power, it's very competitive. But if you normalize it, basically dollar per kilowatt, there's no question is the best by lot.
We love that. And the efficiency is still great the efficiency because of all of these little innovations.
Awesome. Well, Balazs, thank you so much.
Another interesting thing, Balazs, maybe you could talk about. These are not identical. It's not the same piece on the other side. You see how the helix
because it's the force balance.
You could explain why.
So the no axial.
It helps with bearing
most
load,
of the bearings are just have no active radial load because they are either cancelling out because of the nature of the planetary, or they are cancelling out because of the opposing helix angle.
So that's where you can spin it too. You can get a pretty high top speed without worrying.
Mechanically, that's one of the reasons.
And one thing is, our rotor, and Balazs and I worked on this a lot simulation-wise. Do electromagnetic simulation, Balazs do the mechanical simulation, and that close, collaboration led to a rotor that we can spin to 20,000 RPM without any wrap, carbon, wrap, and carbon wrap adds also to the air gap. It's more like insulation layer. So you want to have the air gap optimized as small as possible, if you manage to spin it fast, and because our air gap is 0.65 millimeter, which is one of the smallest for a permanent magnet that spin at this speed. That led to more power and torque densities.
So what Brad works with me closely on the inverter designs, and so on this one of the important electrical aspects that I always have to get across to the mechanical engineers is to reduce the loop inductance. So I always have to explain, what is loop inductance? What does it come from? And it has to do with when there's a current flowing in a conductor and returning, by another path, it's how much the area is open in there. When the current forms a loop, then that becomes an inductance. And if you could flatten those loops,
it's a magnetic field that creates undesirable effects. Which is you can speak about that.
The undesirable effect is extra inductance.
It's extra inductance, and the extra inductance, what is it?
Well, so if it's involved in the switching loop,
the overshoot,
So if it's involved in the switching loop in the inverter, when it's in the switching loop, the the current in there must start and stop. And when there's inductance, inductance behaves a little bit like, sometimes I like to use these mechanical analogies with electronics. It doesn't always work, but like it's a little bit like a flywheel or water in a hose. And when there's this water hammer effect when you slam the valve shut, it could blow the end off the pipe.
It's a flywheel. It causes delay. It doesn't actually necessarily cause losses. It causes delay in your current and voltage, and that's during switching. It would lead to an overshoot of your voltage spike. So what it means is that if you have a 900 volt, let's say, battery pack, your inverter will be switching at, let's say, your overshoot will be 1300 volt. Right. And then you break the chips with that. Yep. You want to keep the chips to be in their domain, which is, let's say, 1000 volt or 1100 volt. So reducing the loop inductance would make, we're uniquely high voltage, so we make sure the loop inductance is super optimized,
that's right.
which is a mechanical electrical process.
That's right. So like Brad helped, the mechanical engineers were involved in getting this DC link capacitor made, and so there's some, you can see there's a lot of parallel, there's twin conductors on each of
so
these.
typically the inverter, you get the voltage bus, voltage terminals from the battery, and you put in between them a capacitor.
Yep.
And this is basically we call it the DC bus capacitor bank.
Yeah, so the DC comes in here, and this is a pair of capacitors, and then, because we have 6 modules in this inverter, so one set of modules goes on this half, and the other set goes on this half. I don't know if we have a cutaway of that one, but both polarities are here. There's the positive tab and the negative tab, and you see they're arranged in such a way where they are, there's no loop area in there, so the return path is right against the source path.
Awesome, Dick. I think that's good. So, and Brad, you'll be leading the team. Yash was working with you back to design the system, and now you have, of course, a much bigger team. We're going to introduce Jonathan and Taj in a few minutes. But Yash, I know, transitioned to a new role recently, or almost a year, 2 years ago now. Recently,
like
recently in my world. And Yash, from the conventional inverter, you can simply explain what is that in terms of architecture.
Sure.
And then you transition to the boost, even in few words. I'm not sure we can maybe add a drawing later on to your conversation.
We can do a drawing.
Well, you can do a drawing, they put it in the video maybe.
I think Dick and Emad did a good job about explaining what an inverter is and what are the main components, right? We have the DC link capacitor, we have a bunch of stuff that converts the DC to AC and ultimately drives the motor. And in changing the inverter from just doing motor control to now doing boost conversion, we have to add a whole bunch of stuff. We have to basically intercept the current path from the charger to the pack and then do a bunch of stuff to it and magically turn it from 400 volts or whatever the charger was outputting into the pack voltage. So we had a lot of ideas. There's a lot of ways you could do this. And I think we chose probably we looked at what do the customers get value out of, like what would be the most valuable thing to do for the customers. So we had a whole bunch of solutions that maybe didn't deliver the best charge performance or compromise maybe in the port location, but we ultimately said, well, what's the best thing for the customer? We did the hard thing, right? We moved the port, which was like an enormous, challenge in and of itself. And then we basically ripped up the inverter and motor gearbox, and we added a whole bunch of stuff to it to get it to do this conversion. That's all of this, So what all of this allows us to do is we basically, the charger doesn't go to the pack anymore. The charger goes straight to the inverter, right? And the inverter has a bunch of contactors. And all these contactors, what they allow us to do is, if you were to plug into a high voltage station and actually charge the pack natively at the pack voltage, the contactors in here actually bypass everything. We call that bypass charging. So we bypass all the stuff in the inverter and we actually just connect the charger straight to the pack, which is the easy thing.
Explain that here
Sure.
quick.
Yeah.
This is the input from the charging port. Yeah. So I hope I'm not messing this up, but this is the input to the charging port. The contactors, in the case of where you have a charger that can meet pack voltage, would come out here, the output to the battery, the high voltage connection. If it can't directly go from the charger to the high voltage battery and match the voltage, that's when you go into the boost mode, which then actually does the boosting in here before it outputs back to the high voltage battery, just so people can see exactly where it is on the actual unit. Here you go. Thank you.
So that current path it looks similar from the outside of the drive unit. So the charger connects to the same place, and the pack current comes out the same way. But if you were to plug into a low voltage charger, these contactors will change the current path so that the current from the charger enters the neutral point of the stator, which is over here. We had to add a neutral point. Normally our stators are Y connected, which means that the neutral connection or neutral point of the stator is floating. And we had to, you can see the old stator and the new stator. And the new stator, we had to actually bring out this neutral point.
We had to intercept that neutral point and connect them together and share that with the inverter. So basically, in an inverter, typically you have a DC bus and you have a bridge of switches to switch to three-phase. Now that three-phase will be actually your one side or terminal, combine it together. So this will be combined together, and the other side will be your returning path of the current will be the neutral. And I think we showed the drawing. I know it's harder to explain, but it's a completely different architecture. The boost is nothing to do with anything that the motor does, but you still need a stator and the rotor to filter your harmonics because that's your inductance right now that you need in this case. It's a useful thing to have. So the higher the inductance, the better and the smoother your current from the charger is.
We could have actually built a separate box that did this.
Yes.
And if you stare very closely at the circuit diagram of a normal boost converter and you compare it to the circuit diagram of an inverter connected to a stator, it starts to look very similar. With one or two, little modifications, you can turn what a motor and inverter into a boost converter. So that's what we decided.
So we use the same set of switches, same coding in the inverter, same controls. The main thing is just the contactors to basically connect the terminals together and have a return path. The contactors and some controls. That's the added change.
Yeah.
Everything is the same common. Simple. Simple.
I can do it in my garage.
Yes. Brad and Jonathan and Taj. Thanks, Yash. Thank you so much, Yash. Yeah.
If we just lift this guy off, set that over there.
So that's the
This is the boost subassembly. This is actually the new capacitor that's going into this drive unit, and what it's replacing is these two capacitors and all of the Y caps and filtering elements that we have on the back. So all of this is built straight into this capacitor
without compromising power or efficiency.
Yeah. And it ended up, it's much smaller. You can kind of see the difference in the size of the two. It saves us a lot of weight too. And we're able to actually use a lot of the space that we saved from going to this to package the boost unit on top of.
Boost subassembly.
And we can show the old version here.
Yeah, that's the old inverter with the film caps, old caps, and this is.
And in just a pretty much identical space, other than this chain.
Right.
Yep.
Yeah, Taj and Jonathan, how you realize that this packaging and is it 6? You designed this in a couple of months, I know that. Yeah. And then you have to release. We skipped all conventional design cycles, but we did it right.
We have this big ask for all these new components we're going to put in. There's like almost 3 kilograms of components in here, and it's like, I want to put it all in, but you can't have more space. Well, it's kind of tough. So, we got a little bit here. We say it's like about a coffee cup worth of space, but other than that, we're kind of stuck with what we have. So we just kind of go into every component, just like the capacitor, and we just try to take as much space out as we can, take out all the space from the remaining components that we can, and just shove a bunch of stuff in there. So, we're trying to get as much power density as we can out of it. So every component here.
So the biggest challenge I remember, of course, is to basically have no compromise basically in performance. AMI, packaging, and we always said we're going to have 500 amps because the current is 500 amps, and then with that space you're going to get your bus bars to be capable and thermally capable and cooling in the right way, and then you're dealing with certain components that we never sourced and the size, and in this short time frame we were able, the team brilliantly really like imaginatively find a way how to still put it in that space, because we're constrained with some vehicle. The Gravity was already designed,
Right.
basically released for production.
Right when Tesla opened up the
Yes, when the Tesla opened up the network,
Yeah.
and working super hard with you know you know to make it happen with this aspirational performance. It's very aspirational.
Yeah.
Taj, what role? You know, you've been working with Jonathan and Brad and a few others in making this happen, and you know you've been. The other day I saw you in the lab. It's like, I made it happen. I can do it. I was like, okay, this guy.
So yeah, work with Jonathan and Brad on the mechanical design and some of the validation work. So as Emad said, the bus bars that you see here that connect all the contactors are carrying a lot of current. So the full charger current, 500 amps at the charger. So they need to be able to handle that current throughout their entire lifetime, which takes a lot of validation work that needs to go in to ensure that they can do that reliably. So every single subassembly that will go into a customer vehicle will be tested as a burn-in test to ensure that all of the high current joints are fully validated and can withstand this current.
And there is no degradation sometimes because of thermal expansion. Vibration, we have to go all vibe tests because, you know, we have to do a vehicle, we do it in the computer, then in the lab, and then the vehicle. And this short time frame.
Yeah, crazy.
And we've done all that. It's a huge achievement. Thank you guys. I think this is gonna be transformational for our customers, our company, and I think more to come. Of course, we're working on the next things, and glad Kyle, Jordan, and team here have seen your work. Ram, welcome. How long have you been working together? 9 years? 9 years plus? Yes. You know, Ram and I, and then Rushaw, which is, come over, Rushaw, come over. Hey, Rushaw. Also, hello. You guys joined the same year, or Rushaw was a little bit earlier?
He's 1 year.
Well, we joined the same year.
Yeah.
Rushaw and Ram back then, of course, remember we sat together looking into flux maps to control induction motors and how we get that from simulation as a first step. Had lots of discussions about optimizing efficiency, and then of course lots of challenges with controlling induction motors at higher speeds, and then we transitioned to permanent magnet, and we saw the beauty of how actually permanent magnet they bring lots of challenges. Permanent magnet motors, they bring lots of challenges in some ways, back EMF and high controls, and we talk fault conditions, but they are easier to control from a torque and speed and efficiency point of view. They're kind of easy. We gotta made it happen, but then and now can control it. Can we make it safe? And then we started that, and we're bringing Ram here and Arusha in relation to the boost, especially. But I think it's good that you a little bit highlight your background.
Yep.
Why you joined Lowe's, and the years that we worked together, and then would be cool also, to give us a little bit perspective, the work your team, Ja and Harsh, did with access or integration to Tesla's supercharging network. We don't have to go into the very greedy details, the secrets, how we do it. What Ja said earlier, we don't have to go into those details, but high level, and maybe you can take it from here. Tell us a little bit about your background, and we go from there.
Yeah. So I joined Lucid at back then it was at Eva in 2006.
And Dick, you come over because Dick and Ram has been working how long together? Huh?
So we started our journey with generation 2 inverters. That's when very first inverter that Dick started working. Then to generation 3. Now we call it as generation 4. I always wanted to work for EVs, and at Eva was a perfect opportunity for me. Joined as young senior engineer. Now I'm group
director.
So for motor controls, and it's an amazing journey. Regarding the product, I'll let Rushaw. Rushaw is the senior manager for motor controls. So
but you are very technical too. So you can speak technical. You can speak technical.
Love that we're all here. This is great.
Thank you.
Sorry for just having one.
Yeah, Rushaw, you lead a fantastic team. That they made it happen. I call them the wizards. Tell us what the wizardly stuff you have done to make the boost especially happen.
Yeah, so at the time we wanted to go to NACS, to get access all these charge facilities across the US. we had to solve this one problem, is how we can charge 800 volt battery with like the 400 volt supply, right? And without like stacking a huge like power electrons in the car, because we have like, a space concept, we don't want to ruin that. So like the hardware team, Emad's team, come up with this super fancy idea of like reusing the rear motor as the the inductor to boost up the voltage from 400 volt to 800 volt. With that said, that we need like a very sophisticated control algorithm behind that to be able to control these currents and voltages, right? So my team is responsible for like writing that control software. So my team member Harsh and Jia and a lot of other engineers work together. Hong Yan, and and across team there's like charge teams and a lot of
Shan and his team.
Byung-sang. So we have worked very closely, and we come up with idea like how can we work with the Tesla charger, demand the current and voltage.
Yeah, and the main challenge with Tesla, Rusha, by the way, Rusha and I appeared in a video together when we were doing the 400 miles. It's on YouTube, in our channel, YouTube, 2018, 19, 20, I can't remember exactly, 20 maybe. We did the 400 miles in one single charge, and we were super proud of it. Yeah. And he was next to me in the vehicle. And
the co-pilot.
He was my co-pilot. Yeah. And in regard to the challenges you've had with Tesla is like, especially there's a certain criteria with DVDT that Tesla applies for safety, parking. And then switching between cabinets can create some challenges for boost. If you charge with a normal battery, which is stiff voltage, you have no issues. And I think what your team was able to do is just this during basically the transitions between cabin to back cabinet, you were able to really create a new novel control algorithms that are. What is your success rate now for?
So yeah, we face this challenge, right? Like
in the beginning we were but now
we are like struggling with like what's happening. But then we designed this algorithm that we don't care what Tesla is doing at all. Like we are very insensitive to what they're doing, but we are smartly be able to control the voltage to a level that we're never gonna trip their DVDT detection, while be able to hold that voltage and current. To charge our battery. So that's
very cool and important. Well, thank you, Rusha and Ram, Dick. Of course, these three and myself, we were, Dick is still, of course, very well. We still are, but we have been exploring all this new control strategy, new electromagnetic. Dick, you've been working on all that cool stuff related to the dead time in the inverter with Ram and Rusha, how to make it more efficient. The dead time is important for.
We're still cooking up new ideas.
Yeah, always. FPGA, what's our advantage in the FPGA side? If the FPGA, right? You Dick, of course, you designed the FPGA, which is. Is it commonly used in all, or not everyone uses FPGA?
I don't really see it much anymore. Early Tesla designs had a FPGA out there too. So on the board we have this is the main processor that controls where all the ROM software is in there. And then this one here is an FPGA, which is a field programmable gate array. It's a logic. It's like a hardwired logic device.
It's a logic, but it's basically hardware and software logic. But I mean hardware capability with software capability.
Well, yeah. So it's like a freeform palette of logic gates. It's just flip-flops and NAND gates and stuff like that. And then through the language we call Verilog, we design circuits there, and we could test them, and then we download them into there. So it behaves like hardwired logic. It's not like executing a program.
Yes, not executing a program.
It's a bunch of stuff in parallel. And so like on our design here, the FPGA, it works together with the software, and it's involved in things like synchronously sampling the state of the drive unit. So it's making a simultaneous measurement of like about a bunch of different things like the rotor angle, all the phase currents, the current.
Basically, it's very important for fast responses, right? And synchronization of sampling, and it works alongside the motor control unit, which is another computer in the inverter.
And then, so then in an area where it kind of steps in is in the case of, it's challenging when you have a permanent magnet motor, the fault conditions are more challenging than they are on a induction motor. Because on an induction motor, almost every response, you just stop switching the inverter and the field dies down and the thing just coasts. But depending on the conditions on a permanent magnet motor, you could get conditions like on a slippery road, you could have some negative torque event. Yeah, it could try to slow you down. And so we try to avoid that. So the FPGA monitors a bunch of conditions and it determines which switch might have failed or something like that.
Yeah.
So it jumps in really quick. And so these two chips, they kind of work together and they help us when we study something called functional safety. Sometimes it's important to separate a safety function into two different areas so that a single failure doesn't take out your function.
What's beautiful here is because we have it all in-house, we do over-the-air updates all the time to improve robustness and do changes. I mean, how many times we had changed even during Gravity launch now, the algorithms to make it better and robust, and we keep always improving either performance or robustness or efficiency.
I think the coolest thing, Emad, it's of course a testament to what you've done here, but no other car company would let us do that.
Oh,
that was so cool.
Oh, thank you so much.
I think the viewers at home are excited. There's still so much more to talk about, explore, and do other things.
I think we would probably transition to the battery team just to talk a little bit battery.
We should also look at the graph, if we can, of our supercharging session.
We will show it.
Yeah.
We'll share it. That's actually available right now.
Great. And then, I think the biggest thing is so many different boosting technologies or split pack technologies to interface with Tesla are out there. This was not the easiest solution, but you went through all this craziness just so that you can sit flat at 220 plus kilowatts.
Yes.
And I think to us it's so easy, just say give us more power, let's do it, right? And then we're like, great, it shows up at the office for us to test. I'm like, great, they did it. It must have been so easy. All of this was crazy.
I hope you have more appreciation of this.
Yeah,
and your audience, of course. And fantastic.
Because the biggest thing to stress here was all of this was just for interfacing with Superchargers.
Yes,
basically.
Frankly.
Yeah.
Yeah, no,
because you could already boost
and here is the
before.
thing, 1 year.
Yeah, crazy.
When did we talk about it?
So we were together a year and a half ago.
A year and a half ago.
Yeah.
Yes.
And you were like, how fast should it be on Superchargers?
Yes.
Because this was right when
back then we didn't even make it happen or decide to do it.
Right.
Just like what would be an acceptable, let's say, charge power rate, and you said I remember start with 2.
Numbers got to start with a 2.
200, and here we are 225 kilowatts.
Well, and the Air was never designed to really interface with Supercharger because they weren't open.
Design it correctly.
Yeah.
for that infrastructure.
Right. So it was the only chargers that were not 1,000 volt were 50 kilowatts.
Exactly.
And you could do that.
Exactly. So not over design and
Yeah.
But we're super. All those very hard. It's actually much simpler in other ways. We can go to other, like for example, split pack will have a balancing always thing that you have to take care of. So this when it's working, once it works, it's more like the engineering control phase that's hard about it. But scaling, all that.
Now that the hard work's done, you're ready to rock and roll.
Yeah.
Very cool. Well, this was to me I'm sorry to the viewers it wasn't filmed super seamlessly, but it was one of the most fun things we've ever done.
Yeah, this is the way. This is the Lucid way.
And the video's not done. We still got more to do. So let's go do that. Well, guys, you can all leave a nasty comment below for Emad because we just went through some of the most incredible laboratories, battery labs, looking at jelly rolls. We went through powertrain, dyno areas, which was incredible. And you wouldn't let me film.
Yes, but of course we always want you to be excited for the next visit here.
Yeah,
we got you an opportunity to film the booth, which is you're the first time to film it, by the way,
cool.
and talk about it.
Yeah, thank you.
Yeah,
and
we're
thanks for the tour.
Yeah,
the tour was cool. In case you're wondering, we saw so many.
We want you to come back.
Yeah,
get another one. But now we're going to talk about what.
Yeah, so essentially what we wanted to do was, this video is all about charging basically of the Gravity and a lot of the stuff behind it. On our testing channel, and we've probably included some stuff in this video, we have charged the Gravity ourselves at a supercharger and a high power charging station. And you guys were cool enough to actually pull the data off the vehicle.
Yeah, and we're going to share it with you.
Yeah.
The raw data.
And we're going to see it all. So can't wait to show. What we're going to do is start with the supercharging stuff, but we'll walk through this with some of the team as well.
Yeah.
But, it was just so cool to be able to see all that
I think we fulfilled I have to say, a wish that you had is like, hey, compatible with Tesla, bring that convenience to our customers. Starts with 2, which is 200 kilowatt plus.
Yep.
Peak and sustained, and we're going to talk about the sustained performance.
Yeah, this is a long sustained. So
Yeah.
we'll get there. We'll explain all the numbers to everyone. But this is really like what we have to do on our side. We basically, you grab the data from the car and just hit some buttons. So made it way easier.
Well, yeah, and of course, this is our strength, right? Like we have a data team. We have, that fast pace of getting things from the vehicle and in our computers to analyze and act quickly if needed. But what maybe the best people we have here to explain this charging sessions best, I have with me 2 brilliant engineers, 3 actually. Shriram, you should be joining us in a minute too. I have a Blake who is leading our system strategy and technical implementation, and then I have Greg who is leading and technically responsible for our battery systems, powertrain systems, both strategy, optimization. 2 brilliant, best of the best.
Yeah, these guys are awesome. I've known them too. They're really cool. So glad we get to bring them both.
Yeah, you can. Greg, tell us. You've been with us for a while too now.
Yeah. So
Blake. Yeah.
So I think it's been over 4 years now.
I remember the first time I had a conversation with you was in a drag strip.
It was
in Sonoma. What's that?
Yeah, we were doing some air sapphire testing.
It's like Greg comes to me. He's like excited. It's like we can optimize this. We do the torque.
Yeah.
Like, who's this guy? Seems like has potential. This guy. Because you were hired earlier, but I didn't get to know you much.
Yeah, it was an exciting day. I think we had just unlocked, over 1,000 kilowatt on the battery, and we had just tried it on track, and we were all really excited to see that.
9 seconds.
Yeah. It was an airplane, so yeah.
Hell yeah.
And Blake, you've been with us also around 4 years, I believe.
Yeah, 4 years. I was actually hired to do onboard charger software.
Yeah.
And then now
Blake,
how long have we been working together?
Whenever with the challenges with Electrify America alone and every other charging issues,
surge.
Yeah, you go to Blake, he would tell you modestly, I think it is this one, but I'm not sure. When he said that, that means it's sure is that thing. It's like it turns out to be like accurately so. I was like, and recently he moved from that role. I pulled him in to be more systems lead because he has so much technical depth in charging.
Yeah, I've got involved in all kinds of things from like plug and charge, for example. What's the user experience of charging? How can we improve route planning, all the things that very dear to your heart. We watch a lot of out of spec here, so we take it all very seriously. I think plug and charge might be a good thing to talk about with what we're looking at behind us. Because before we even start with any of those graphs, when you were plugging in, you plugged in the charge gun, and then you said, oh, wait, I need my app.
It's going to be putting in a lot of work. Let's see how it goes. And a 3, 2, 1. Nax port is in. Oh, I've got to activate the supercharger. I'm silly. Let me do that. Oh, it's plug and charge. Oh, amazing. So, plug and charge happening.
Wow, why are we here?
And then it starts charging. No, you don't. We have plug and charge.
How does that work? What is the different protocols, of authentication? There is plug and charge. There is EVgo has another protocol. In Europe, they have some others.
Mac ID.
Okay. So we're going.
Why we have all these protocols? Why not one? Why
it's going to be a 5-hour long
video.
Just quickly. Okay, so I'm curious. So in terms of automatic authentication experiences, so when you just plug in and you don't need an app, you don't need a credit card, anything like that. Really, 2 competing technologies. You have ISO 15118 plug and charge, and you have auto charge. So auto charge is MAC address based. So when your car connects to the station, it sends a unique identifier. It just sends that to everyone, to the world. Not the most secure implementation, perhaps. We've seen all sorts of problems that other OEMs have run into where maybe it's not unique for every single car.
Right,
and then you
Mazda,
have to,
not to name names, but there was one guy that got billed for every MX-30 charging session at EVgo one time, is my understanding. There's not many of them out there, but
it's a cool feature. However, it is not the the ideal way of implementing that.
Yeah.
We have been plug and charge since the early days of Lucid Air with Electrify America, and now we have that same technology still with Electrify America, but also with Tesla.
And so, do you want to mention also that having from accounting point of view, how does this work for our customers? You have one account for we call it Lucid Charging Network.
Yeah, absolutely.
Yeah, so, we talked about this yesterday, and you're like, there's just one certificate in the car.
Yeah, so
which is crazy.
Yeah, so we got one certificate in the car. We got one certificate in the car, and as a Lucid customer, you just sign up for a Lucid charging service, and that works with both Electrify America and Tesla. With
one credit card, one account.
One credit card, one account, no duplication.
Yeah, we charge us with both Electrify America and Tesla Supercharging work with PNC, but of course we can charge with other networks,
Of course.
Either apps.
Of course, but with plug and charge, we were talking about the technology, we were talking about auto charge. Maybe that's not the best secure implementation. With plug and charge, everything is encrypted with TLS security.
Yeah.
We have a great cybersecurity team here who have integrated all of this PKI stuff.
So Blake, I think we should transition to the next, from plug and charge to the interoperability testing. You were involved very well with the motor control team, with the cloud team, and for others, but overall, what do you want to say about that? We don't have to go into all details. We went through some details overall, but what is interoperability testing usually? And when do you have a acceptance level of sign off? You say, I'm good to go. Roll it out to customers.
Yeah. So
there's
charging,
success rate and all that.
So charging is fascinating in the sense that yes, there are standards. However, we have to be open to a lot of different behaviors. If I'm designing a system that communicates between a battery pack and an onboard charger, that's pretty deterministic, and I know both the guys who are writing code for both of them, and if it changes, we can change them together. But with charging, we don't have that luxury. The charger is going to throw at us whatever it's going to throw at us. So we do interoperability testing in a bunch of ways. So probably we start with conformance to standards, ISO 15118, J3400, the new SAE standard which standardizes NACS. So we have means of checking that we conform to those standards, and then once we have conformance, we go out into the world and we test with different pairings. Now
you go to Charin.
We go to Charin. We're Charin members.
That's where I met you, actually.
That's actually where Kyle and I very briefly met about a year ago.
Which is a very useful example. I remember you always tell me, I actually performed interoperability testing, for example, with the Rivian charging network, and he said, it should work. Ionna, another. So it gives us that confidence. We have.
Exactly. So these events, it's like a round robin. We have 10, 20 chargers in one place. Vehicles rotate around doing 1 hour slots. That's useful. We go to labs around the country.
Blake, let's in brief about especially with Tesla. And interoperability testing was key for us, of course, before Referral. And it was more challenging than normal because of the voltage, compatibility.
Of course.
We can, go into details forever about this topic. But briefly, I think, in 1 year, we were able to not just, of course, fine-tune the controls. We were able to add PNC, plug and charge, and complete integration with our Lucid app, which is a feature. So convenience to our customer, Kyle and Jordan and team, is like hugely important, not just, of course, performance. And we were able to achieve an amazing success rate with a very short amount of time.
Yeah, absolutely.
We exceeded what Tesla required. Tesla required certain level. We much more exceeded that.
We require a certain level of plug-in success. So when you plug in the charge gun, how many times do we get to a certain metric? Perhaps reaching current demand and more than 1 kilowatt hour delivered. And we had engineers around the country plugging in, making sure that we were confident that we could do that every single time in every condition. Now, of course, we worked through issues.
Yeah.
I don't need to talk about
Yeah,
all of them.
well, yeah, we went through issues.
We went through times when we were plugging in like, oh, no, this is failing on Tesla specifically when it wasn't failing on other charging stations. And we had to partner with Tesla and go back and forth being like, this behavior is different to what we see on other charging stations. We talked about the lightning fast handshake time. We had a few issues because in some cases it was a little bit too fast for us.
One thing is like, for example, the ISO check, you know, how Tesla does ISO check and, you know, making sure the voltage matching our boost voltage. That was a challenging problem.
It was. You know, I think about charging sometimes as like a flight. You have a takeoff, a cruise, and a landing. And they say about flying, the hardest parts are the takeoff and the landing. The cruise is pretty easy.
My job's the easy part of it.
Not to disparage what Greg's doing over here. But no, once we're stable in the session, like, of course, there's a huge amount of complexity in sustaining 220 kilowatts for more than 15 minutes.
That's engineering.
Amazing curve. But from a robustness perspective and a success perspective, the places where we see issues are typically the start and the end. So, we have a lot of strategies for optimizing that.
The biggest advantage we have is that we have in-house hardware and software and OTA capability to act root cause quickly, because we root cause it internally. And fix it, roll it out second day. I meet with Blake and Greg and team. It's like urgently, it's like, hey, we have faced this issue. Build a new software. Tomorrow we're going to test it. Tomorrow we'll be in Tesla charger and test it. And oh, it works, but we still have this. You know, it's amazing. Thanks, Blake. I mean, Greg, you're responsible for that longer phase. It's not this.
The flight. The flight.
The flight.
I'm more of a flight kind of guy.
Which means the performance.
Exactly.
The performance and optimization.
Exactly. So I think on the theme of, you know, charging is such a big world, and a big part of it is really just the charging experience, you know? And so charging experience can be the plug and charge, it can be the interoperability, but a big part of it, of course, is, you know, what is the charging performance and capability? And a big theme for us with Gravity was, you know, I mentioned to Kyle, is consistency. And consistency in a lot of different areas. You know, first thing is consistency with the different charging networks. And so enabling NACS boost charging meant that we have performance consistency on an even greater scale of different charging infrastructure. And so we actually have here...
Wait, don't you talk about the...
Yeah, let's look at the graph.
Before we get here, Greg, maybe you can tell us a little bit about just the preconditioning strategy of the car. Because in order to get this, like you mentioned, you have more repeatable temperature windows. The temperature window, because this is only like about half of what the car can do, it's not as important for this. But.
So preconditioning in itself, you know, Shreya and my team works a lot on that, and it's a very complex world because you have competing systems. Different systems want different things, and so you really have to figure out how do I balance it across the different systems, and that's even more of a challenge when you're trying to do boost charging.
Systems including, of course, drive units, battery, efficiency, your range, and so on.
The thermal system, the cabin, a lot of that. So there's a lot of different inputs, and
preconditioning can be to heat up the battery or cool it.
Exactly.
It depends on the case.
Exactly. So preconditioning wise, you know, we can't get into the details of the numbers, but generally speaking, batteries like to be warmer to accept higher current. However, you also have...
What's our temperature range? At 200 kilowatt, what's the temperature, roughly?
Yeah, so we can usually sustain it over, as long as it's over 20 degrees Celsius, we can achieve these performance figures for that power level.
That's pretty low.
That's pretty low.
That's pretty low. Yeah.
And that kind of goes back to actually like development we do in the cell to make sure that the cell has this consistency.
Much wider, you know, basically bandwidth for to accept charging compared to industry benchmark and even our earlier cells.
Exactly.
We expanded that or extended that significantly.
Exactly. And that kind of goes back to the theme of consistency. Another theme for consistency was temperature consistency. So, you know, one of the big things there was ensuring that we had consistency in cold weather, in colder battery temperature starts where maybe you don't have the ideal, you know, temperature, whether you didn't manage the precondition or, you know, you're just in a rush. But also in hot weather, in extreme weather, having the ability to, you know, start hotter and still not, you know, degrade in your performance. So again, consistency in temperature was a big theme.
So in a normal day, let's say 10, 15 C, for most customers who would charge at Supercharger, they don't need to precondition because you will get almost the same performance, which to me is important because not always you want to precondition and wait and people are in a rush and all that. I think we you know that band, you know, widening and, you know, it's so important for us.
Yeah, air was pretty temperature sensitive, at least in all of our testing. We always talked about making sure we were
more, but cold too. It can be.
And there's been a lot of innovations to get to this point. You know, it's one of them is the cell. Like, you know, we've co-developed a cell and really took all our learnings to make the cell better, you know, at these cases. But secondly, at the system level, you know, our system heating capability,
sizing everything and optimizing the pack chiller,
exactly,
the AC compressor.
Exactly.
You talk about that system because you did that optimization with the team, huh?
Yeah. So, you know, one of the things we did maybe almost 2 years ago, you know, we create these Pareto fronts where we basically try to understand, you know, how can we improve fast charging without, you know, busting the bank. You know, what is the cheapest way to improve the fast charging? And so, you know, we look at hundreds of different parameters, and one of the big ones is related to the thermal system. And so that's why, you know, part of our investment into Gravity was really improving the thermal system because it gives us a lot of advantage both from a heating and from a cooling standpoint. And again, gives us this, you know, wide range of consistency.
So heating is more. We increased the heating, preconditioning power.
Yes.
And we improved with cooling significantly.
Correct.
And the cooling is a chain of actually from starting with the air intake in the front. Hugely improve it. The radiator location, hugely much more effective in exchanging heat with the air. And then, of course, the chiller and all the other...
Our compressor change and all that.
How we change it also, split the cooling circuit between Wonderbox and we change it from air. So many lessons learned.
Cool.
We just re-optimized it and reconfigured it.
And you know, there's some extremely talented guys on the thermal team that do the thermal controls because even there are so many different
mentioned to
positions.
Adam
and Yusuf are, I mean, they're wizards. They you know, it's some of the smartest guys struggle to keep up with, you know, people that are just experts in their area, you know. So, you know, there's
Naeem and his team.
So, you know, they've done some really great things, and all of that comes together. It all comes back together to get this experience to be as great as it is. And so here, you know, we come back down to boost charging.
So, Greg, I know you showed me some data. If let's say in a hot day, 35C, 40C, you know. Let's say it starts with a normal day, 15C to 35C. Cabin, you can charge. You can turn on the cabin. Charging performance doesn't get impacted. That's correct me if I'm
correct. That's correct.
You go to 40C. If you don't turn on cabin, you get no effect on your charging performance. If you turn on cabin, there's very minor change at very high stage.
Death Valley. Turn off HVAC, the thing's still going to rip. If you have it in like pet mode or whatever, it's going to still prioritize cabin a bit.
Exactly. And that, you know, a big part of that is having more thermal capacity at the vehicle level meant we can do a bit of that splitting to make sure that, you know, we still create a nice, comfortable space in the cabin while not completely degrading the charging performance. And, you know, we've done some extreme tests, you know, with high solar load and, you know, all these kind of crazy cases, you know, driving the car really hard, charging, solar load, you know, high cabin setting, super hot weather over 40 degrees, and the Gravity just takes it. It just,
we're going to show it. We're going to put it in the worst case against, but we'll also do it against the competition too, so that everyone's there. We plan on doing a lot of SUV comparisons, and one of them is drive the shit out of the cars, excuse my language, plug them all in with HVAC on max and see what happens.
Yeah, we're excited to see that. We're excited to see that. So.
We're thrilled to, independently to verify would be the right way. Yeah.
So this is the session. Oh, the one thing that we talked about as well that is interesting is when you navigate to the charger.
Navigating, routing, Yeah, so, as I mentioned, preconditioning is important, especially in cold temperature, and hot too, but cold is even more important because you can't even charge. So that's a must capability in EVs. I mean, if you don't, but it's also a must to have it automatically, done during route planning or navigating to a, place or to a charger. But still, we would like to optimize and reduce the preconditioning time, as well also the energy lost during that phase. Don't spend. So when you're out to, based on, we have the charging, algorithm, which sends a signal to preconditioning. During route planning, Blake, you can come in here. We know where you are routing to, if it's 400 volt or 1000 volt, and also which station we have. Right now we have some static data we know which is charger, but we're going to have dynamic data coming also for navigation. So we know it's a V2, it's not going to be included in route planning. V3, which station is available, not that's coming soon, very soon, in our navigation. However, what we included is that if you are going to a 400 volt, just go low. What is needed for preconditioning? Only what's needed. And automatically done that. If you go to a 350 kilowatt or 400 kilowatt station, it preconditioned to the right temperature. So you want to, of course, to understand where an SOC you are and all that done automatically.
Manual preconditioning setting. So you also offer the manual, right? So which is cool. What does that target?
So we're starting with something. Very cool. We talked a lot this. Stay tuned.
Okay.
We're gonna have advanced menu someday.
Really?
Yes.
So I can have like a pre-chill before driving?
Yes.
There's been some really cool talks. We're excited.
Some cool talks related to that. Related also to indication of what's your charging power when you arrive or during that. So some algorithms are coming for really soon. You saw our energy app. It's very nice what we got today, but it's really building on top of it. Because right now we have a platform for that.
Good. So updates to come to manual preconditioning, it sounds like.
Which is well, manual preconditioning. Not every car has it. Like very few who has it already.
Well, you can always manually precondition with the throttle or the accelerator, right? But you actually have a button that does it, which is nice.
As long as you have no passengers.
Right, exactly. You can get car sick real quick doing that. All right, so this was our session yesterday. So let's walk through what happened, and if people want to see more, they can go to out-of-spec testing and just get the raw data.
So this was a boost charging session we did yesterday.
It was at a V3 Plus site, so it had the V4 dispenser with the immersion cooled cable. I was really worried about doing it on a V3 because Emad keeps telling me this thing's going to have a fat charging curve, and I'm like, we're going to smoke V3 cables. So we needed the latest dispenser. So we went to a site in Milpitas, right, somewhere around there. And we got the car basically as soon as it dipped from 1 to 0% SOC. Temperature window super wide because we're barely stressing the battery here because the battery can get all the way up there. So we were good on temps for the most part. And Greg, maybe walk us through what the heck we're looking at here.
So you can see here there's a few different things happening. So first of all, what we're doing here is
why don't you start with this one? I'd like to start with
SOE,
but with the state of charge. People call it SOC. They're very similar.
Of course.
State of charge or state of
energy.
They're similar.
So big thing again on the theme of consistency was to get a flat kind of charge curve and really ensure that we enable that to high state of charge, which is especially a challenge when you're working with battery packs that are also getting high energy and high range. So that was a real big challenge for the team. And again, lots of things went in there to extend that curve to go further out to the right. The kind of secondary thing is we're also managing two things here. We're managing our drive unit system, which is doing the conversion, so stepping up the voltage.
And the drive unit system, which is 2 times more powerful than anyone, and it's almost half the size.
we got to recognize the level of power and how long you sustain that.
Absolutely, yeah. I mean, this is just continuous load on it, basically.
Yeah. So I think that was a big thing. So consistency and, besides being consistent and operating over such a wide range of state of charge, it's also at a very high power level. So 220 kilowatt, we definitely wanted to be over 200 kilowatt. And so we kind of came to this optimal power for now of 220 kilowatt.
I love it.
And
you saw some units still in the lab there.
Yeah, still more work to be done. But it's still boogied pretty good. One thing we should say is like the time, for example, from 10 to 80 was, what did we say, 28:04, was it?
Yeah. About 28 and a half minutes. Yeah.
With
and that's faster than Jordan's Model 3 natively on Tesla. Not to knock anyone here, but I just wanted to say, even though we're well under the peak performance of the car, the curve is still fat.
Correct.
Maybe, Greg, with the 16 mod, with the Touring, we will get faster.
Yes.
We will get faster than 28 minutes.
Yes.
Maybe we don't have to share the number, but it's going to be a few minutes faster.
Yeah.
Because so smaller pack will be even faster.
Right.
Significantly.
And we'll explain why that is on the next slide with the voltage.
Yes.
I would think it's going to be maybe 25, 24 minutes. Huh?
We could probably achieve.
Yes.
Let's leave it for later.
Yeah. But that'll be on the smaller battery pack.
Yes.
But that's more comparable to the Model 3. You brought up the Model 3.
Right. There's a much bigger battery pack. There's 123 kilowatt hours.
And I think that's also the impressive thing, of doing this, almost 28 minutes charge time, 10 to 80. It's also on a fairly large battery. So in terms of the amount of energy throughput we're delivering over time, that's significant.
It's the range, basically.
And that's why, when you look at the range, so if you look on the left-hand side, there's also, there's a little table there. Yeah. You can see
this is EPA rated, but as we said earlier in the conversation, real world should be close at 70 miles per hour. I mean, there are variation, weather and conditions and tires and all that, but 80 miles per hour, of course.
So when we do the 10% challenge, the numbers will be different. This is also a car on the Aero.
Yeah,
this is also Aero wheels on the car.
Aero wheels.
The one we had was 22, 23, which these numbers would be different, but just to be transparent.
Exactly. And so when you look at this, you can see basically, what ultimately the customer really cares about is how much miles of range can they add, over a certain amount of time.
Absolutely.
And so that's really the ultimate, decider of how great that experience was. And you can see, despite this not being our, highest power, highest performance native charging session, we're already leading class just with this capability in terms of the amounts of miles of range you can add. And that's, the combination of, how we develop the battery pack, the efficiency of the vehicle, the range we're getting out of it, and the, boost charging capability, which is best in its class. It's unheard of being able to do this kind of boost charging in a non-native form for 500 volt network.
Well, so there's a couple fun stats that I'm not here to really shit on anyone else, but for example, Rivian cannot hit this peak at all, and you're holding it longer, and this is in your boost profile. So that
non-native,
right? And they're native there. You're non-native, and also. I forget where else I was going with that. But then you look at the Korean stuff, and that's half the power almost.
Correct.
Not quite, but almost.
Yeah.
And also a lot of interoperability issues that I've experienced with their cars on Superchargers.
Yeah.
And we talked about DVDT and all the other things, maybe why that could be the case. But basically, just even with this on the Supercharger, just smokes almost everything.
It does. It does, So, this again, it's an amazing performance. Maybe we can go into our really.
How is this possible also thermally, and why we sustain this? Maybe the next chart would show you. That constant voltage.
So this is what I've been wanting to show, because when Tesla logs in and looks at this graph, they're going to be so confused. Because what the charger can only output
the charging voltage.
This is all Tesla sees here, or whoever has the low voltage network, right? And so normally when you charge a battery, you start at low voltage, and then it comes up as you reach higher.
Basically similar to this.
Exactly.
Similar.
This is all you're telling the charger. You're just putting it at its max to reduce losses.
Exactly.
And that's the huge benefit is when you get the small battery gravity, which this, pack voltage is going to be shifted down. It still means that your boost charging stays consistent. And that is magic. That is so cool.
Absolutely. Speaking about starting, in this case, from 700 volt, you're in about with 120
20, 30 volt.
Yeah.
So that you know that during that you accumulate lots of heat because to get to same power you need to increase current to compensate it. And most of either vehicles derate or the charger would derate in that case.
Yeah.
So to increase voltage and keep it constant, the maximum voltage, hey Tesla, hey charger, what's your maximum voltage you can take?
Yeah.
450 volt, for example. Okay.
Yeah, and leave a little error, margin of error.
We leave almost 10, 15 volt, like just noise or variability from charger to charger and things like that.
Totally.
Just always.
But that's all worked out through the handshake process, of course, through the
100%,
communications.
100%.
Car says, "Here's what I want." Charger.
Right now for about 450 volt constant in all chargers. We don't vary that. We keep that margin already baked in all cases.
Yeah, it's super cool. And then of course so this is what's basically the charger is seeing, and this is obviously the vehicle is stepping up the voltage to this level here.
Yeah.
You can tell, the bottom of the pack, just like with all chemistry, really trails off at low SOC. Yeah. And so we had the dip down to basically just under 700 volts dead. And I think today we even maybe were a bit lower. We were in the 6s when we started on the high power charger. It was really down, but pulls up the voltage so quick.
Yeah.
And even with that insane rise, because you have to compensate in such a short period of time for this massive voltage rise, totally stable here.
Yeah. And I think that's really the power of boost charging in our architecture is you have the ability to vary this boost ratio, right? This boost ratio is basically the difference in the kind of proportional voltage difference between, the output voltage, which is what the battery is seeing, and the input voltage that we're getting from the charging station. And as Emad was referring to, even if you have a smaller battery pack and lower voltage, the boost charger can deal with it because it can deal with variable voltage ratios. And so we can still push really high power, very similar power with a smaller pack. And so the smaller pack is actually benefiting even more in terms
that's
of
even
its
better on a supercharger.
C-rate capability.
So to the end user, though, miles added per minute is the same.
Exactly. But with a smaller bag, you get it with the same with a smaller bag.
Yeah, of course. Yeah.
Which is some benefit.
A couple questions.
Don't wait for tuning. Grand tuning is better. See the next slide.
Just get a Dream Edition.
Just get Dream Edition. Yes.
Okay, so we've got 500 amps ripping.
Yeah.
And we get into CCV somewhere around over here.
Yeah.
Do you want to talk at all about any limitations or anything that could be happening? Because it seems to be sustaining 500 amps for a really long time.
Yeah.
The big qualifier here for me is we did this on a V3 Plus station with the enhanced cables and the enhanced cooling. You do this on a regular V3, you probably smoke the cables somewhere, around here. What do you think?
Can I come in on that?
Yes.
So we tested on a V3 Plus because we know that has improved cable cooling, but we have been talking a little bit as if you wouldn't see this on a V3.
Yeah.
A lot of times we see this on a V3. You can do this on a V3. Not every time.
Yeah. Maybe not middle of summer.
Maybe not if you're doing 0 to 100 runs, but most people aren't doing 0 to 100 runs.
They aren't, They are usually 10, 15%, start 20%.
Exactly. So you plug in at 10%, you plug in at 20%, you plug in at 30%. You still get the max power.
But that's the advantage. Other vehicles maybe would derate even starting at 10, 20%.
Exactly.
To pull that, because, maybe, I mean, it depends on what, because Tesla limits at 500 amps today.
Everyone else can do 500 amps, but Tesla vehicles will do like 700 amps on V3 Plus, 700 amps on V3, 900 plus for Cybertruck on V3 Plus.
Yes.
And you smoke the cable.
Yes. But that's right. You have this flat voltage here. We're already, even if we're at 0% state of charge, we're close to 450 volts. So we only need 500 amps.
Do you communicate? But you must communicate also SOC to Tesla through the comms.
Yes, we do.
So that must be so funny to them. That's not unusual because the Koreans also do something similar. So
they do. It must look funny, but we're asking for amps and a target voltage, which we set a little bit higher than what you see there, just to keep the charger in a constant current mode, and keeps it pulling at 500 amps.
The battery's just chilling along at 250 amps, basically. There's nothing for it.
We'll see in the next graphs and when we go to the high voltage to show you the picture of
Now this is the session from today. So this was at ChargePoint Express Plus, which kind of almost got us all the way to 400, but it was a little station limiting. Not maybe only by a few kilowatts though.
Maybe are we requesting 405 kilowatt or 400 plus? What are we requesting now? I mean, we can say.
What's the theoretical?
So the theoretical limit is 405.
Okay. 405.
For our system.
Yeah.
We have never had our car in front of an EVSE that can do more than 400.
But when we went to Ionna, we did 400 kilowatt. I'm going to share with you the graphs. Yes.
Yeah.
Alpi on it.
Yeah. So
and we were requesting 405. We were station limited. It says it's station limited there.
Yes. So there's this thing in charger communication where the charger expresses a limit to the car, and then the car asks for.
I see.
So we would not strictly request more than what the charger advertises.
I see. So that's the same thing. But I know what you mean now.
So the car would know, and it could show limited by station, but the station couldn't show this.
Exactly.
Exactly. That's the thing.
Yep, got it. I think our viewers know this too. We've covered this quite a bit.
Yeah.
Okay, now this, I just want to point out, monster session from today. We had I don't know, 20 people around the car charging. All the charge point people came out. It was really fun. So much excitement. Again, out of spec testing, but this is all the data. You don't have to watch that video if you're watching this. Okay, so we were up here at huge power for a long time.
Yep.
This is a little bit unusual to have this little dip and up. What was going on there? What do you think?
I mean, there's a lot of things that you're managing at these kind of high power levels. And so, you're balancing thermals, you're balancing voltage, you're balancing the current. And so there's always going to be a little bit of ripple there. But ultimately that kind of average power getting close to 400 kilowatt is what we're really trying to get there.
Overall, it's smooth.
Yeah.
We're maintaining over 350 kilowatt up till almost 32%, if I see in the graph here.
Yep.
30, so that's pretty good. Over 350. Yeah.
Yeah, it was 300 kilowatt to 40.
Yeah,
that's great.
350 kilowatt to about 32, and then above 40%, above 300 kilowatt.
Yeah, and so for the 10% challenge, for example, as we start at 10%, you're gonna have so much area under the curve.
Yeah.
This thing's just gonna be a monster. Can't wait to see how it does in that test, of course.
Yeah.
Some other interesting things I noticed during the charging session were, and we'll get back to this in just a second, but you rate the vehicle as 926 volts, resting at 100%. But under charging, we're at 938, 939.
It goes to 940. It depends case by case.
Yeah, but you might see close to 940.
Yeah.
And I was like, what the heck? That's awesome. That's so cool.
That's not uncommon, right? Sorry.
That's not uncommon. Yeah, the charger pulls us up. It's like you need a voltage gradient to deliver the current, right?
And you also worked with ChargePoint. We remember, I'm sure our viewers will comment too, we can never get errors to 100% on ChargePoint chargers sometimes for range tests. That's solved now. Okay. Yeah, great. We're good. And it was maybe because you overshoot a little bit the communicated resting 100% voltage, not to go super into details.
Yeah. So, we were communicating 926.
Yeah. And ChargePoint's like, oh, why are you up in the 930s?
And then, ChargePoint was like, wait, what? You're at 940. No.
Anyway, but that's why charring events happen. That's why interop is so important.
And it's why we partner. Like, we don't just develop this in a vacuum. We're talking to Electrify America, we're talking to EVgo, we're talking to ChargePoint, we're talking to Alpatronic, we're talking to everyone to make this the best experience we can.
Yeah, so back to the numbers then. Greg,
we want to get the numbers.
So here we go.
Yeah, so I think,
actually we have it. 350 kilowatt for over 7 minutes, pretty damn good.
Yeah.
300 kilowatt over 10 minutes, which is up to 41%.
And I think when you look at it in the time perspective, this is where, again, some of the magic's happening, because the power versus SOE curve is amazing as it is, but it doesn't tell you the full story.
It doesn't tell you capacity.
How much
exactly?
It doesn't say capacity.
Right.
It's a tiny battery or
exactly.
Like an energy added, but that's basically what this is.
Yeah,
correct.
We should have that.
Yeah,
we can provide that.
Yeah. And so that's the magic, is where we're able to do 400 kilowatt charging with over 120 kilowatt hours of battery capacity. And when you combine those two things together with a vehicle that is super efficient, you get, again, that customer metric, which is the miles per minute added, and you get that being, again, best in class. And so if we look at this, we're talking about adding 100 miles in just 5 minutes.
Yeah. And that's from our session data.
Yeah.
From EPA testing. I mean, we'll do the similar thing with our 70 mile per hour test, but Air almost matched EPA in 70. You think this is going to get close to EPA, Emad?
we haven't tested it in a real world because
at 70,
we're at 70. I think the team has, but it's going to be close.
Yeah.
It's going to be similar trend. Yeah,
Can't wait.
Yeah.
So this is actually pretty realistic based off of our prior Lucid testing.
Yes.
Yeah. That's the point I was trying to get across.
Yeah. So we're really excited. I mean, you're getting down to absolutely in the theme of no compromise that we have with Gravity. So you're really getting exceptional
Should we
capability.
say how we're gonna do it with espresso and coffee, or that? Keep it there for
Let's keep it for later. Let's keep it for later. Yeah.
Come on.
You got to keep Kyle on his toes,
we need to get that ad for us. Well, anyone can do that anyway.
Yeah.
So maybe only Lucid can do.
Okay, cool. Yeah. So we know we're adding like monstrous miles. I mean, 300 miles of actual driving in under 20 minutes.
Yeah.
People don't want to drive more than 300 miles at a time.
Exactly.
That's perfect. That's the way to do it. I mean, just an absolute monster charging vehicle. What else is there to say about this other than we should mention like fan noise was super quiet.
Yeah.
Compressor is unbelievably quiet.
Yeah.
I mean, I didn't even know it was on. And then Blake's like underneath the car. We're like trying to listen for it. Meanwhile, it's pegged at like 7,000 RPM or something. You can barely hear it.
Yeah.
This is the improvements. Like we learn so much how you mount to the compressor on the vehicle, on the drive unit, and all that. And that's same case for the drive unit, how isolated it is, both front and rear. And the compressor has to go through the same type of mindset in terms of isolation, because it matters a lot, especially with charging, right? It's like you don't want to go and cross the city on like AC is all and wake up the entire restaurant there.
Yeah,
it's like,
yeah. Who's screaming out there?
So it's super quiet. Super proud.
It's very impressive, especially compared to the entire competition. I would say maybe GM does a pretty good job, but they're about it. And they just probably put a million. I don't know. I'm not here to knock them, but there's a lot of foam around there. Anyway, this does a good job being quiet. Yeah.
I think it's worth saying maybe some people are watching this thinking, well, this is great, 400 kilowatt charger. I don't live near a 400 kilowatt charger. First thing to say is there are a lot more coming. We're really excited with all the new installations we're seeing. ABB, ChargePoint, Alpatronic, all around the country.
V4 with Tesla.
And
Tesla,
of course, Tesla V4 cabinets.
Yeah.
We've already done our
Can't come soon enough.
with Tesla. We can't wait for 1,000-volt Tesla stations. So it's going to be huge.
Yeah, absolutely.
But while we're waiting, or maybe you're waiting if you don't live close to one, think about what this means for a 350 kilowatt.
Yeah, you see that.
Yeah. You'll get your power versus time. It will be up here. Sometimes we even see more than 350 kilowatts.
Right. So
power
we've seen, I can say I've seen on like EA Signet stations like 370, 80, whatever. So it should be the same here.
If Electrify America doesn't change it, you should see the same.
Right. As long as they don't limit it.
We've seen it too.
Yeah. But you'll just be pegged basically there until that point, until you intercept.
Exactly. So you lose a little bit of area under the curve, but not a lot.
Not a lot.
Not a lot.
So based off the infrastructure out there, it's just going to be able to max it out and hold it, which is awesome, which is perfect.
Exactly.
So I also just think it's important to bring up, from my perspective, we've shown some crazy charging cars on this channel recently. Lee Mega, Zeekers, Golden Brick, 5C charging, whatever. And I don't know if we can say, but I just saw a Lee cell just for benchmarking. Can I bring that up?
Yeah, you can.
Okay. It's interesting. So we need to do we're going to do a podcast on the trade-off and balance between a power cell and an energy cell. And if you could easily engineer this to do a megawatt charging if you wanted to, but you'd have way less energy density.
Absolutely. I mean, that the technology is available. It's not like breakthrough what we've seen there. First of all, we have to understand as a business and company what the best product attributes we should offer for our customers. Range is still important, very important.
Yeah,
and that
huge range.
A huge range and amazing charging curve that maxes almost the infrastructure basically. And with that, the cost. Add that to cost. Energy cells, which means higher range. Interestingly, the dollar per mile you pay for the cell is much better than power cells, which we explained a little bit in the chat earlier. It requires much more copper, heavier packs, and you can claim that number and then get all vehicles with that added shipped cost, but not well utilized with the infrastructure.
Sure, of course.
And your range, you're not, and we know home charging and all that, the other areas where we factor that into account. But what we achieved here is that we showed that chart. I think we probably at some point share it with you. we're trying to pull that energy and power density way up. So really, and that's what the Gravity achieved it to a large extent. We still keep doing that to make sure we don't compromise the range, at least for the foreseeable future. Now, of course, we're not saying every vehicle has to have 400 plus miles. But what about cost? If you bring a vehicle that's 300 miles, but it costs $10,000, $5,000 more than the 400 miles, is that a better value for the customer?
Yeah,
that's a question. That's the question.
Yeah.
You know, and that's, to get 100 miles, roughly, say EPA in 5 minutes, 200 miles in 10 minutes, we think this is already amazing. And what 99% of customers, in my view, maybe not the 1% like Kyle.
I actually totally agree, because you're maxing out all available infrastructure installed publicly in our country right now. There's no need for more power because you couldn't get it anywhere. Now, we could always ask, hold it longer, but that would be the only real benefit. And, for Gravity, this is a car you can still get to with such a fat curve. You can get to a charger at 10, 20%. You don't have to run it to zero and still get a very meaningful charge session.
When the other charging curve, which is much flatter, it's already amazing numbers. We're talking about, how much 100 miles and 200 miles and 200 miles in 18 minutes or something. That's pretty damn good.
And keep in mind, for a lot of people with Gravity, they will want to use superchargers just for the availability, for the native port. The benefit of using high-power charging station runs out at about 50% state of charge. Anything 50 and above, it's identical.
So, our CEO recently said it's the best damn car. So I think we made charge. We attributes to the vehicle overall are amazing.
Yes.
But the charging shines in many ways. It's the plug and charge, route planning. You saw the features, and then of course compatibility with 500 and 1000 volt networks. We will continue to innovate, both for the current platforms that we have for Air and Gravity, but a lot happening and exciting stuff coming for the midsize. We can't wait to show you more stuff there, Kyle and Jordan and team. Maybe next visit, hopefully we have midsize revealed, and we can talk a little bit more about that. But for now, hopefully our customers and potential prospects for Gravity know that this vehicle nearly achieved compromise nothing. Probably did. I hope you realize that.
Yeah, absolutely. I think it's fun to make fun of you guys for the compromise nothing thing, because everything's a compromise. But
I know what you mean.
But it is, try to compromise nothing is what it really should say.
Yes, absolutely.
But that's really fun. So all in all, I think what this video really showed is what I really loved, because we went into this not knowing what the heck we were going to film today. So it was really fun. We got to meet the people responsible for how the Gravity charges and drives, and that was really awesome, and hang out with you guys who are like awesome, resources to have it just in the overall automotive industry. We got to, of course, charge it, which was awesome. That's mostly why we came, was to do a DC charging session on Tesla, because that's so important to the Gravity customer. Seamless charging, lots of availability, no question the best network out there, but a huge problem of having a voltage limitation on all of their chargers today. And then we did, big boy charging, and we had to literally go to a lab to find a powerful enough charger to do this. But thankfully, high power charging infrastructure is rolling out very quickly, especially now that Alpi's here, now that Ionna is doing their thing. EA is going to be using them. ABB's got the A400 coming. Big power is on its way, more split systems with big site-wide power sharing, and this thing's just going to be a monster. It is, it's the highest power passenger vehicle charging in the US, and I can't wait to see what it does in the 10% challenge. No question it's going to be the best SUV. Actually, we should almost run this and Escalade same day side by side. That'd be kind of fun, just to show the difference of efficiency. But anyway, just thrilled with what we were able to see, thrilled with you guys and hanging out with you all day.
We really enjoyed, always these conversations with you, Kyle and Jordan. Always appreciate the feedback, the positive and negative, to just always keep us improving and pushing.
Always. Well, you'll always get that from us, and it's tons of fun. So plenty more to come, but thank you guys for watching and joining this sort of behind-the-scenes charging tour nerd deep dive. I wish we could have
been as open as possible, and
absolutely.
we do this. Well, I really appreciate you coming here.
Yeah, thank you. And yeah, we got to see a lot of stuff we couldn't show the viewers, but
yes,
it was all awesome. It was just so cool. So thanks, Emad. Thanks to Nick on comms for making this happen, of course. So shout out, Nick. He was in my dad's video recently, so go watch that. I'll leave it linked. Yep, and we'll see you all in another one again soon. Bye-bye.
Thank you. Bye-bye.
Thank you.